watching the Weather Channel, your most accurate and dependable source of weather information 24 hours a day.
Hey, good evening. You're watching the Weather Channel here on a Friday evening. Chief Weather Jeanette Jones, and as we look out there, Jeanette, look for
Like that, kind of?
Yeah.
Okay.
I think that works.
Okay.
I'll do your. Welcome everyone to day 2 or 3, however you want to count it. Was Monday day 1? I guess so. Welcome to our planetary protection session. I'm so excited about this one because as astrobiologists, we don't always think about the geoconservation of things. And it's something we all need to keep in mind. So I think this is going to be very informative. Our first talk is by Sarah Swers. Talking about the case for conservation of outer space, an analysis of conservation as a planetary protection strategy.
Thank you. Okay, is this volume good? Great. Okay, thank you guys so much. Okay, yeah, so today I'm going to talk about conservation of outer space from a policy perspective. And I am going to talk about that, but I'm also going to make it more of a broad talk today about how the humanities and interdisciplinary research theory might inform your research and maybe spark some ideas for how you could collaborate with other biophysical scientists and then maybe people outside of the biophysical sciences. So this is quite the pace change maybe from all the other talks. You guys have been sharing such wonderful science and kind of engineering information, but this is just a fun way to maybe kick off the middle of our conference and hopefully you leave with some different perspectives. So first off, I don't know.
My bad.
Oh, you're all good. Well, my next slide is talking about this image. This is called Manifest Destiny. It's by a painter from the 1800s. And you might keep this in mind as we roll through the policy analysis perspective on conservation. And then I'm from the University of Central Florida. I'm starting my second year in a master's program there in interdisciplinary studies, and I focus on law and policy and ethics. So I wanted to start with this image to kind of set the tone of maybe what we're doing as astrobiologists, or at least back when I was doing the science. I kind of like this, it resonated with me, and then also now when I do more of the social side of things. Sometimes it does feel like this, sometimes it just feels like days are long, but there is a major element of curiosity and open-mindedness and empathy, I think, that comes with an interdisciplinary field like astrobiology. This is the Flammarion engraving. We don't know who did this. It popped up in some meteorology textbook in France in like the 1800s. So just an interesting idea to ground us. Yeah, so today it's going to be a broad talk, and I hope you walk away with something that might resonate with you. So we're going to talk about planetary protection from the space law and policy perspective, the issue of ISRU in situ resource utilization, and how that's going to pop up and maybe affect astrobiologists, conservation as a policy strategy, what's up with that, and you'll hear a lot more later with one of our other talks in planetary protection, humanities and interdisciplinary research in astrobiology, what are some benefits, a little bit of my experience and how I've really enjoyed that. And then colonialism and planetary science. That's what I've learned from my interdisciplinary research, and maybe there's some insights you all will want to take away today or think about. So planetary protection policy. There's two main ideas grounding this. There's backward contamination, which is the idea of preserving the integrity of the Earth's biosphere from contamination from any sort of space life forms. And then there is frontward contamination, so preserving outer space environments from contamination by Earth, organic compounds or life forms. These are the two grounding principles and kind of the reasons why behind planetary protection, why there's whole offices, there's whole UN talks about it, and a lot of funding that may or may not be affecting your research around planetary protection. And something to note too in the policy space is that the transition or handoff or interplay between like public and private research and government research is a big deal here. We have a lot more private sector work in space after decades of the government nationalist space race, and that's going to affect planetary protection because frankly, we don't have a set legal limit or kind of enforcing body that can really go hardcore on enforcing planetary protection. So that's kind of the policy context, kind of the law context. Now let's think about the economic potential of space. So in 2023, the space industry was valued at $630 billion, which is a lot of money. There was like a McKinsey report and a World Economic Forum report saying that in, I think, the next 5 years, it might be at like $1.8 billion with all of the prospective technological advances. And a lot of this money is coming from plans for expansion into sub-industries that are built around space resource utilization. And a lot of that is resource utilization for exploration of space without having to continue to go back and forth, between Earth and outer space. Could we mine resources from the moon? Could we mine resources from asteroids to take us on this kind of like space highway? So you could think about maybe 50 years ago in rural America, there might be gas stations along the highway that get you from somewhere in the south. I'm from Florida, up to the northeast. Well, that's kind of the idea of development here. And this is kind of intertwining and sometimes opposing scientific, government, and industry interest as we have more public or more private driving of this development of the space economy. This is just a little reflection moment. What is the value of the Apollo 11 landing site? Like, what would it be worth? What comes up to your mind? Is it a number, a feeling, a fear? I don't know. So that's just an idea as we think about the development of the space economy in this broader planetary protection context. So now let's think about the extractive potential. We know that we live in a global economy based on extractivism, where we extract resources from resource-rich areas, some of the geology side there, and then we bring them and we bring them around the world in different trade patterns and sectors. And so the idea behind the development of the space economy has a lot of extractive language tied to it and a lot of extractive logic. We're talking about shifting from kind of the satellite hanging that's driven a lot of space economy over the past couple decades and a lot of space concerns around orbital debris to now resource identification and utilization infrastructure, which is quite different. And that involves intense interaction with planetary surfaces and bodies, which could really affect our science or our scientific opportunities. And then also thinking about national interest and national security, that's a lot of the language too, militarized language or the way we frame other countries and our interactions with them or relationships with them. This you can see if you Google like lunar helium-3 mining of the moon, there's a lot of national security interest or framing around that. And then also infrastructure development. So like we said, gas stations on the Great Space Highway, what's gonna take us from point A to point B without always having to come back home here. I hinted at this, there's potential effects on our scientific inquiry and capabilities. We wanna do science, people wanna do development. There's a lot going on there. And it also might affect how science is doled out and how science is given a priority or not given a priority. I know this seems like a pretty pessimistic take. There's also opportunities, right? Maybe for things to coexist with private development and exploration. So I wanna, lend a thought to that too, but I'm just pointing out maybe some potential roadblocks or issues that could pop up from our scientists' perspective. And the societal effects. This is just a really broad issue. There's a lot we could think about with how space mining could affect global society and socioeconomic inequality or flourishing or health here on Earth. That's something informed by our current global distribution of resources and the way our economy runs, and it could really be affected if we add in this huge influx of value and materials and money from outer space. So that said, here are just some reflection questions related to ISRU, in situ resource utilization. So kind of the space highway, how are we fueling ourselves and getting resources? Just some stuff to think about, and thanks to Erica for helping me come up with these questions that might be relevant to you as a scientist or engineer. You can take a moment to just read them. Maybe something pops out to you. And if you really like these types of questions, maybe you would like policy work. But yeah, so transitioning on, a policy solution, often in the literature, the space policy and law literature, people say, okay, conservation, like we do it on Earth, right? We do it a good amount on Earth, maybe nowhere near enough as we should, but this is something we could do to protect lunar and outer space environments. And there's some strategies, which they might sound kind of fun or funky, but this is really like stuff people are saying to do, and it really is just kind of mimicking what we do here on Earth. So space park systems, very much like our national parks. This coming from a US perspective, but I know these are successful in many countries, and I'm sure we've all had like many wonderful, beautiful memories, hopefully, like at national parks. So a similar idea to that, establishing more World Heritage sites, but considering expanding what we talk about as the world. This could be inspired by a precedent of like the dark night sky, the idea that that's part of our common human heritage and like protecting that, which is great for us astronomy-oriented people. And then also really important for people's cultures and ontologies. And then looking at extraterritorial region law and policy. So extraterritorial, that just means like research, like what they do like in Antarctica, or how we have the law of the high seas, or like the law of our climate, or like the atmosphere, which are regions nobody can really own. And it's not like we can just tell the UN, solely to govern that. So we have some precedents from how we've dealt with research or resource utilization in those areas of the world. When we think about conservation terrestrially, though, it's usually in a reactionary sense, right? It's reacting to the impending or pending threat that's constantly there of something being enclosed and extracted and used, or something not being used responsibly, because that's just how economic incentives generally work in a global sense. And so keeping that in mind might help us when we think about conservation in outer space. Are there some logics or some experiences that we're just replicating and doing Earth 2.0? Are there ways to maybe reform or make things better? Or is conservation maybe just not the best framework for us, or maybe it's really useful? These are all questions that maybe someone from the humanities or a policy analysis perspective would ask and want to think about. And so one useful kind of critique or critical perspective is the myth of the frontier, which is entwined with imperialism and colonialism. If you grew up here in the States, this was in a lot of our messaging, whether that's interesting TV shows or in classes at school or AP US history. This is just a big part of it. And it kind of relies on the idea that there's a terra nullius, or there's a nature or an earth or an environment separate from human activity that ought to be preserved or overcome or managed. And that logic underlies a lot of what we do in terrestrial conservation, and we might repeat those ideas, which we could say might be ethically undesirable or not just in outer space. So is there a need for conservation? The whole point of what I'm saying here is that conservation in itself, while we've all had probably many positive experiences with it on Earth, for sure, and seen it maybe protect our home, local environments, or something else we want to save for future generations from destruction, it's not necessarily in itself like a morally good thing, you could argue. It's something we do in response to other human activities, and the need for it is shaped by how we construct our economies, how we construct our social processes. And so it kind of lives in a bigger idea. So if space exploration continues through an imperialist approach with the language and the function and the economics of that, conservation, yeah, we could repeat it, and it could be a great way to help us. But there are worlds where maybe we don't necessarily need conservation as a policy approach. But if we're going to move forward in this extractive way, it seems like we are, we should really consider it as an important policy strategy. But we can also be critical of where it's coming from and the limits of it. And also, I'm not saying conservation's bad, by the way. Again, it's not necessarily good or bad. That's not the argument today. It's more just to provoke thought about the context for why or why not we could use conservation as a policy strategy. And where do we go from here? So this is all kind of stuff that I'm thinking more or that other people are arguing, but interdisciplinary work really helps us see how our science fits into the bigger picture. It helps us see how maybe our goals of objectivity in science, or that kind of standard that we claim to enforce, may or may not line up with how other knowledge systems in the world are working. And that can be scary or confusing, and it can also be an opportunity for sharing and growth and improving our science, and also just improving the world in all pursuits of human knowledge. It's also important to collaborate with social scientists, law and policy people, which I've heard so many people already talk about their interest in personally doing that or their experiences with that. I think there was a talk yesterday, Michael, where you're literally collaborating with philosophers, which is amazing. So yeah, and then also maybe most importantly, a little self-reflection on our values and our experiences in the world, and understand where imperialism is inherent to the processes of funding, research, development, language that we use, and understand that there are other perspectives in the world, even though the dominant perspective is so dominant. And we can do our best to listen to those voices, center them, and respect and uphold their rights to exist and be a part of our conversation. So at the end of the day, context is just really important. It's something that sometimes in the hustle and bustle of being a scientist or an engineer, trying to get funding, churn things out. Sometimes we lose sight of that, and so it's good to be aware of the context for what we do, the social context, and that's what the humanities can bring to astrobiology, I think. Again, this was not, a super dense idea here today. It's more just to provoke thought. Where can maybe the humanities or social sciences inform your work or provide a new perspective? And because I'm getting my master's in interdisciplinary studies, I sometimes am like, what does that mean, right? My little sister jokes like masters of none, like Jack of all trades, masters of none. But I think there are some skills that come with interdisciplinary research theory. This is a field people work on, or like the science of team science, science and technology studies. You might have heard these things at your university, or a social scientist or practitioner of the humanities talk about these fields, but really the skills that underlie interdisciplinary research, kind of like the competencies that cross-cut them, are things like empathy, taking perspectives, understanding complex adaptive systems and resilience, translating between different disciplinary vocabularies, and identifying context. So these are all just skills that I'm sure you all develop every day in science. These are inherent to scientific processes, but maybe, just like lend a second or a thought or reflection on how you feel like you're doing with these, and if there's opportunities to improve them, or maybe ask others for help or learn from others. And I would love to hear your stories and learn from you about those too. And then I know we're coming to the end here, so I'll wrap it up by saying in my interdisciplinary research experience, I did work in undergrad related to climate loss and damage policy, which had some interesting cross-connects with like astrobiology and space policy, especially in that extraterritorial sense, like who owns something or can legislate something. And so there was kind of some work I did on decolonization from the perspective of a settler trying to understand what that idea is and how to engage with it meaningfully. So here are some ideas that are important there. And then also my future work I'm hoping to work on is common objections I've heard. This is just very anecdotal, of people when they hear about decolonial theory, which is a very practical theory about repatriating land back to people. It can be something we think of, psychologically, or that we support, which is important, but at the end of the day, it's about centering Indigenous peoples and letting them have rights to self-determination. So I want to work on kind of providing some response to fellow scientists and engineers about maybe some objections they're feeling to that. So yeah. I would like to acknowledge Sam Baker and Amy Liblu de Bartola, who were my research partners years ago when I first started this research. Amy used to go to AbGradCon back in her grad days. And I thank you all so much for listening. Again, this was just to provoke thought, so please let me know your thoughts.
Hi, Alexia from Cornell. That was really interesting. I'm wondering if you could talk a little bit about what work is being done on the policy side in terms of like our government and what the current state is as far as like space conservation goes.
Yeah, I'm not sure of like the current state as of like maybe this last fiscal year, or I don't want to speak to that. I'm not necessarily an expert in that, but I do know that there are a lot of like interagency working groups. This is from a federal perspective, not necessarily like international, but there's a lot of interagency, or there's at least one interagency working group dedicated to like planetary protection. And what that means is it's just representatives from like different federal agencies, or members of academia, or private industry experts who are gonna come together and talk about this issue, what it means for specifically American policy objectives, the current administration's objectives or interests and goals, and then how to move that forward. And I know they produced a report, I wanna say last year. Again, I don't wanna like try to summarize it or anything, because I'm not quite sure, I'm just coming back into this field. But there is work being done. It is not legally enforced or like mandated. There is no governing body internationally, but there are experts sitting in a room talking about it, producing reports. That would be my summary, so yeah.
Hi, Danny Buckheister, Penn State. I was curious about what you've seen of successful ways for scientists to make connections with people in the humanities and invite in people who maybe don't have expertise on the subject of astrobiology specifically, but might have interesting insights based on the work that they do and how that could have links into what we think about. I guess I'm just asking, what are some of the ways that you've seen successful collaborations begin?
Yeah, definitely. One that's like so interesting of a field and something I'm hoping to work further on, like in my graduate studies, and investigate that more from that like kind of science of team science perspective and how that actually plays out, and some of the values or interest or logistics of that. I will say what comes to mind is one, just looking around and asking other people, has that played out for you? How has that played out? Like, I don't think there's really a resource that necessarily gives a guidebook or an outline for how this goes. If anyone knows, let me know, like, in another field or astronomy, astrobiology, space science related. So definitely it's more, I think, anecdotal and just listening for success stories, which I feel like I've heard sometimes. And then also there are some grants or specific situations. I'm blanking in this moment, but there was one astrobiologist, I think his name is Dr. Stephen Freeland, who ran a workshop where he brought together practitioners from all different disciplines, and they did some interesting activities to kind of translate between the vocabularies of the humanities and the sciences. So there's some examples of that, and that was a big report, a very good report on that in 2016. But otherwise, I can't really think of a book or a manual or an example. I think a lot of times it's just those informal connections and then people being willing to do the process of explaining where they're coming from and having a listening ear and taking that perspective. It's not really a great answer, but I can totally email you the link to that one grant.
you we're going to have to forgive me losing my voice today as well. So we're just dealing with that.
Mic issues, okay. Our final talk today is gonna be Fletch, or final talk in this session is gonna be Fletch talking about exogeoconservation of Mars, putting theory into practice.
And I'm going to say I've introduced myself as Fletch to probably everyone here, but if you ever want to find any of my work, you are going to have to use Claire Fletcher, my actual government name. So that's just a quick caveat for everyone. All right, so to get into it, a little bit about me. First of all, I got into geoconservation because I did a master's on the oldest evidence of life on Earth over in the Pilbara and how we would create a roadmap for the conservation of those sites. From there, I got really into Mars, and I decided I would do a PhD on the exogeoconservation of Mars. And right now, if you have no idea what exogeoconservation is, exo for space, geo for rock, conservation is what you know and love. The word was invented in 2018. That's why no one knows what it is. So pretty timely. And I have been looking at both policy and practical aspects of exogeoconservation. So the first year, I was looking at policy. If you are interested in policy, particularly after Sarah's talk, please read my paper, but I'm not talking about that today. Instead, I'm talking about my second year of work in my PhD, the practical elements, which I did with experimental work at the Mars Desert Research Station, where I was for 2 crew rotations earlier this year. So, why would anything geological need conservation? I'm going to take an example from my master's. These sites are stromatolite fossils from the Pilbara. They're 3.5 billion years old, and they've been exceptionally well preserved. Now, these sites have been used as a Mars analogue, most recently in the Perseverance mission, and that is because they are 3.5 billion years old, which is similar in time to Mars's theorized warm and wet period. But their exceptional preservation is not just the fossils themselves, it's the broad environment that you get there. These fossils within their ancient environmental context is key. But even though this is a really important site, it's very rare, ancient, scientifically valuable, there's been significant theft and damage of these fossils. And it's not just aesthetically displeasing, but this is actually a real issue because by removing the fossils from their broader context, we lose information about the environment of early Earth and how life may have formed or evolved in that environment. So why then would Mars need geological conservation? I will not explain to anyone in this room our goals for going to Mars. I think we are all familiar. But what I would like everyone to keep in mind here is that to meet all of these goals, the sites that we need to go to and explore are sites with really key landforms, minerals, paleo environments, maybe even fossils. And what that is describing is sites with geoheritage and that we might want to explore and do our science on, but without damaging like we've done to the Pilbara. And that is what exogeoconservation is. So again, if we use a little example from Mars, this is the home plate digitates, these little white lumpy bits. And they are opaline silica found by the Spirit rover. And this site is an intriguing site because of the morphological similarity to digitates found on Earth. And the digitates found on Earth have been shown to be microbially mediated. So even if you don't think that the home plate digitates are microbially mediated, it's an interesting site because how can pure geology make the same morphology as something that's biomediated? That's an interesting question. And also home plate has evidence of both alkali and acidic hot springs preserved there. So another really interesting geological question. But it's really small. So the digitates occur discontinuously in this area in the dashed line. And that means that small, simple actions can destroy an entire site, like a rocket landing. And even though it's a little silly animation, that rocket is to scale on home plate. That's Falcon 9 to scale over home plate. So there are actually real risks here despite me being a little facetious about it. So I decided for the second year, for this practical aspect of going to the Mars Desert Research Station, that I would look at developing and testing methods of simultaneously exploring and doing exogeoconservation as a way to allow for the effective in situ decision-making strategies guiding exogeoconservation of Mars. It's a lot of words. And so this is what I'm talking about, this practical aspect. And I'm going to mention here that no one ever has done a practical exogeoconservation study for Mars, and certainly not done it experimentally in the field. So that's what I chose to do at the Mars Desert Research Station. And I was there for 2 crew rotations, so a full month living and working in an analog environment. But why MDRS? First of all, like I've said, exogeoconservation shouldn't limit our exploration and our scientific study. We don't want to do that. However, no one will blast me to Mars to explore it while doing conservation work. So I needed a geological analog here on Earth, and preferably somewhere where I can live and work in an analogous environment to what it would be like on Mars. There's also been about 20 years of continuous in situ research at MDRS, and if we look at similarities to Mars exploration and science, it's not dissimilar from the amount of time since Spirit and Opportunity landed on Mars. So there's a lot of data at this site. And really key is that we're mitigating risks by doing this. Not only am I not risking billions of dollars or human life by going to Mars, but we're mitigating risks of accidentally destroying important sites on Mars by trying to test these sort of things here on Earth first. So, a little crash course at the MDRS site. The geology is flat, as you can see. It is very undeformed. For anyone that's a real geological nerd in the room, this is the Morrison Formation that we're in, which is one of the key dinosaur bone finding formations. So it's an extremely well-characterized geological formation. But importantly, flat. And it hosts a series of marine regressions and transgressions, and therefore cool paleo environments that definitely had water, shallow seas, and paleo channels, fluvial deposits. And you can actually see this along here is a paleo channel. And these paleo channels in particular have been extremely well studied and characterized at the MDRS by previous research. There's other geological similarities between this site and Mars. MDRS hosts a lot of concretions of a similar size and form to those found at Meridiani Planum. However, they are a different mineralogy. And it's pretty lifeless on the surface. But what you do have is lithobionts, which you can see in this little green arc in a broken open rock here. And there are the occasional plant or lichen, but mostly lithobionts. And this is all working in my favor for using this as a Mars analog for my exogeoconservation work. So a quick note on methods, and it will be quick. I spent a lot of time before going there identifying what sort of features I would want to look out for conservation, mapping them, planning transects A through D, lots of planning beforehand. And I decided I would also draw up some methods for how I would make decisions while I was in the field. And there's quite a simple matrix and a very slightly more complex decision tree. Don't look too closely though, because now is where I reveal Mars is hard, it all went wrong for a month. Oops. Happens to the best of us. So to get into the issues, the first challenge I had was in our mission operations. You need permission to do everything out in the field, where you drive, where you park, where you walk, where you stop, where you sample. You can't just go and follow the interesting geology. And if you're a geologist in the room, you'll realize that that's a little inefficient, for one, and for two, pretty antithetical to regular geological research. And so for us, what we would do is typically go out to a site, study it in depth, and return, rather than a traditional transect. And this meant that, and for Mars as well, this means that you don't actually have a truly comprehensive idea of what is in an area, only at sites. It's point data versus continuous data. Another challenge that we had was the distance that we could actually travel. I was there in winter. Our rovers were battery powered. You do the maths on that one. That's not an issue for Mars. We've solved that. We can power a rover, that's fine. What is interesting to note is that I personally, over my 4 weeks there, traversed 86 kilometers, which is the equivalent of Spirit and Opportunity and Curiosity to date combined. It's a bit of distance. Over the two crews, 291 and 292, our total cumulative distance traversed was about 480 kilometers. So that's the radius of Argyll Planitia on Mars, or if we want to put it into a local context, it's the equivalent of here to Plymouth. So we went a bit of distance. And even in that time, we could not find all the targets that I was looking for. And we certainly could not predict where they might crop out, which was annoying. And I mean, sorry, I'll go back to this for a sec. You can see we stayed pretty close to the roads. Not always, but generally. And that is because we had some mobility challenges. Of course, it's a suit and you're trying to climb a hill. Anywhere where a rover couldn't go would actually be a risk to human life, we found. But most of our interesting targets were in these difficult topographies, particularly these paleo channels here. So we need to look at some more novel methods of exploring sites like this before risking human life. You want to know that it's actually worth the risk to go to these sort of sites. We also struggle with field ID. If you do anything with your hands at all, but particularly geology, you'll know that having big gloves on and holding things 30 centimeters away from your face through a perspex frame is not helpful. But it meant that we had to take samples. And that's not really what I wanted to do. But it was important to us that those samples told us something if we were going to take them. And so I put a lot of effort into knowing what samples we had back at home, what we needed to know, and what the minimum sample size was to learn that information. I also struggled a lot with the scale of my study targets versus the surrounding landscape. Many of my study targets are in the order of centimeters to a few meters. When you've got a GPS with plus minus 3 meter accuracy at best, that's not super helpful. Mars also doesn't have GPS. And so what was really key was that I was there for 2 crew rotations and we could go back to sites and see them again and use relative positioning to find what we were looking for. And this is also where I note that it's us as scientists that determine what the value of a site is. Scientific value is just made up by us. And that also meant that the exogeoconservation value was just made up by us. And so it changed over those 2 different crews. We also struggled a little bit with record keeping. Papers had indicated that certain databases would be available to us. We asked the director, he wasn't familiar. And we don't know when between those papers being written and us getting there, those databases sort of fell off. No one expects bad record keeping, particularly not from people going to space. But it happens, particularly with time and changes in administration. So the more we can do to stop this, the better. So to summarize this really quickly and give us some lessons for Mars's exogeoconservation, firstly, we can't do exogeoconservation remotely. There is not enough detail in that. We need to do on-the-ground work. But when we're on the ground, it means that we have to conserve on the go because we can't plan it properly beforehand. But conserving on the go, as hopefully I've shown, is kind of challenging and it's also time-consuming. So when we go to Mars and we're sampling it but trying to be conservation-minded, it wasn't important necessarily for us to have the tiniest little sample or only one sample from a site, this traditional conservative sampling method. It was more important that the samples were considered. They actually told us something, and we learnt something new from them. So all in all, we do have a really strong need for a best practice guide for field methods for going to Mars. And there is a role for exogeoconservationists in Mars mission teams, not just present rover teams, but future rover teams and crewed missions. Thank you.
Questions?
What's a paleo channel? Old channel, basically. It is the channel from a river, and it's hard to do with holding a mic. River. And you'll get sediments washed down and cement together. And over time, in this case, we have inverted paleo channels. The surrounding material is softer, it erodes away, and the bottom of the river is preserved now up the top of a hill. So it just allows you to see all the river deposits in sequence. Yep.
I'm Miguel from the Spanish Center for Astrobiology. Thank you so much for this amazing talk. So I was wondering, how is exactly the process of choosing what needs to be conserved? Do you have a set of guidelines, or is there a degree of arbitrary decision on your part? It's both?
So when I first began this study, it was going to be a much smaller portion of my thesis, and it's blown out to be quite big. And this is because I thought initially I would do a literature review from literature on Earth about how we decide what to conserve. And I found essentially nothing. When it comes to conserving geology, the best guideline we have is the IUCN, the International Union for the Conservation of Nature, sets out what they call 7 key elements of comprehensive geoconservation. And they say for any broad area, if you conserve at least one of each of the 7 elements, all 7 in total, you've got comprehensive geoconservation. Those 7 elements are really broad. It's things like evolution of life. It could be any fossil. Or it'll be like representative landforms. So our system on Earth is pretty poor. And so I did use those 7 elements in my study, which I haven't gone through here, but I've identified what I thought would be key features at MDRS in each of those 7 elements. And then I did a more targeted look at those evolution of life elements in terms of what has good preservation potential, those sort of things. But once I got there and actually was doing this study, that's sort of where things changed a lot, because our team values changed. It meant that what was important, what's a representative landform, you know? And that changed because our crews decided that something was more representative than something that I could look at on a map remotely in Australia before coming here and say, oh, I think that'll be representative. So there's no real good system, but even if you try and use a system, it doesn't work very well.
Okay, so I'm sure anyone that's taken a geology class knows that you all the time just go out and see a road cutting and start hacking away at it with no precaution at all. And you're like, how much rock can I destroy? It kind of becomes a game. So I have experienced classes where we go to more ideal sites where we learn about geoconservation and preserving them. Do you think teaching geology students from first year level about geoconservation will make a difference in the long run for the future astrogeologists, or do you think that's just kind of too difficult to put into place on a countrywide or worldwide spectrum?
Short answer, yes. The long answer is that there are some sort of best practice guidelines vaguely about field sampling. And when I say some, I mean 1, maybe 2 in the world, which I tried to do a lit review on and failed miserably because there was only 1 or 2. but there are some sort of guidelines about, oh, do you sample at this site? Do you not? What should you do? And introducing those earlier rather than later, I think is a great way so that everyone is aware that you should be thinking about responsible sampling throughout your whole career rather than just whacking any old rock and taking any old rock. And I mean, if we go literally all the way back to the beginning, this is so annoying. These sites in WA and the damage, this is like, I can't explain to you how middle of nowhere Western Australia this is. And also, I don't know about you guys, but most people look at these and go, that's a wiggly rock. Like, that's nothing. They don't realize that it's an important piece of, Earth's history. And so we presume that these sites are actually being damaged by scientists who want essentially a trophy. It's geology's answer to trophy hunting, which is kind of upsetting, honestly. So the more that we can do to think about that at all stages, and if you are teaching undergrads, bring it up to them. They probably shouldn't be taking home literally like 30 kilos of rocks. Bring it up, tell them. It's something that we can all do a little bit of, yeah.
All right, we are on break until 10:40. Sarah is, no, 10:20. Let me double check. I think it's 10:20. Yes, we are on break until 10:20. Sarah's on her way back with fresh coffee for everyone. You good? Ready? Yeah. All right, welcome back. I'm going to go ahead and get started while people are coming in, just so we don't cut into lunch. Our next session is going to be To Infinity and Beyond, all about exoplanets. The first speaker is Kara Peschiota, talking about prebiotic chemistry from hydrolyzing Titan and exoplanet haze analogs.
Sweet. Hey. Is it on? Can you hear me? Yay. Good morning, everyone. First of all, I'd like to start by saying a huge thanks to the organizers for having me here and putting on such a great conference so far. Round of applause. Thanks, Meg. Cool. And I'd also like to thank you guys for coming out to the exoplanet session. I'm not a biologist at all, but I do love lab work, and it's been really fun to see all of your experiments and what you guys are up to. And today, I hope to convince you that exoplanet laboratory work is also really cool and interesting. So today, I will be talking about my work in understanding atmospheric hazes and what their role is in our broader conversations about astrobiology. So I know there's a wide array of backgrounds in this room, so I'd like to start off very simply by introducing you to my friend methane. sure that many of you are super familiar with this molecule in a bunch of different ways. We've already heard about it this week. But this methane molecule lives as a gas particle in the upper atmosphere of his planet. He enjoys traveling, being an active participant in his planet's methane cycle, and he enjoys hanging out with his good group of friends, including nitrogen, water, CO2, and helium, who all live in the atmosphere with him. His pet peeves include UV light that shines in from his planet's star, and charged particles from cosmic rays or energetic particles that get accelerated in the surrounding magnetospheres. These things are pretty destructive for methane, but unfortunately, he does have to endure them quite a bit. So when UV light and energetic particles reach a methane molecule, it undergoes a chemical reaction called photolysis. So this incoming energy from the radiation breaks apart the methane molecule or photodissociates it, breaking it apart into these, where's my pointer? These highly reactive radicals that can recombine into other molecular species. And this doesn't just happen to methane, it happens to all of his friends in the atmosphere. And since we're no longer just talking about that carbon and hydrogen from methane, we get these really complex molecules that have nitrogen and oxygen in them as well. So these solid particles are our hazes. So to summarize the last few slides, hazes are solid particles suspended in the atmosphere that are produced from photolysis of atmospheric gases. We generally care about hazes because they affect things like a planet's energy budget, atmospheric dynamics, and even surface processes. It can be pretty difficult to tease out how haze affects these things because it often depends on the haze particle's size and composition, but thanks to models, observations, and lab experiments, we are starting to tease this out. One of the coolest things I think we've learned about hazes is that their composition is chock full of prebiotic molecules, most notably amino acids and nucleobases. This means that haze could be a source of organic material when we're thinking about life on other planets, and because of that, we want to study what happens to haze after it forms. So let's jump back to our little haze cartoon friends. Haze is efficiently removed from the atmosphere and falls out onto the surface, whether that's through time or something more efficient like rain. If anybody lives in a place where wildfires are common, you know that smoke that sits in the air, you'll know that it takes either a few weeks or a really good rain to get all that nasty stuff out of the atmosphere. This is the same thing that's happening to haze on Earth and on other planets. So haze is efficiently removed from the atmosphere, is one of the main suppliers of material to a lot of surfaces, and can make up these large-scale features like dunes, or it could find itself in some liquid body of something, right? And I don't have to tell the people in this room how important aqueous environments are for chemical reactions, and I especially don't have to tell you about how liquid water is important for these reactions. So this prompted us to ask the question, what happens to organic hazes when they interact with liquid water? Do their compositions change? Maybe we see signs of polymerization? And can we detect these changes in real atmospheres? But before we ask these questions, I do want to introduce some of these real atmospheres to you. This is Titan, the well-studied hazy moon of Saturn. It has a nitrogen and methane-rich atmosphere that is efficiently photolyzed, and it forms this really thick haze layer in Titan's atmosphere. Now, methane on Titan is like water on Earth. There's a methane cycle and methane rain, meaning that the haze can be efficiently removed from the atmosphere and end up on the surface. We see Titan's surface in this image here. These lighter spots are the dune fields, and these darker regions are the methane lakes. But underneath this surface, Titan has a global water ice shell, and underneath that shell is a global water ocean. So there's plenty of water on Titan, it's just all locked up inside. It would take events like impacts or eruptions of a cryovolcano to expose and warm up this water, and models suggest that liquid water could be stable on the surface for hundreds, if not thousands of years as a result of these types of events. All of these things together make Titan a really intriguing target for answering our science question. Another very unique opportunity we have comes in with exoplanets. So there's types of planets out there that we don't have in our solar system. You may have heard of super-Earths or warm Neptunes. And these types of planets have tentative observations for both haze and water in their atmosphere. Now, in this case, we're using atmospheric water vapor as a proxy for liquid surface water, which is something we think we can do in temperate exoplanet atmospheres. And of course, we'd like to know that for sure, but there's really no way to understand these worlds, since they're so far away, in the same way that we can understand closer in worlds like Titan. But that's where lab experiments come in, right? So we are informed by observations, and we not only want to match and aid those observations, but we simulate exoplanets here on Earth in order to understand these worlds in a way that our current technology doesn't allow. So some of my lab mates have done a lot of amazing work in characterizing hazes on other planets, and their experiments with temperate water-rich exoplanets readily produce haze. And the chemistry of these haze analogs are distinct from our Titan haze analogs, and they're also distinct from each other with only slight differences in exoplanet conditions. So with that in mind, we're going to answer our question, what happens to haze in liquid water, for 3 planets, or worlds, I should say: Titan, a 300 Kelvin water-rich exoplanet, and a 400 Kelvin water-rich exoplanet. First, I will walk you through our haze production process, then our conditions for hydrolysis, and lastly, we'll get into some results. This is the phaser chamber located at Johns Hopkins University. My advisor, Sarah Hurst, built this to simulate photochemistry in a wide range of planetary atmospheres. So we can choose what gas mixtures we want in our atmosphere, and then warm or cool them to a desired temperature. We flow those mixtures through this stainless steel chamber, where it is irradiated by different types of light. So we have a UV light to simulate light from stars, and we have a plasma source to simulate charged particles. Titan experiments glow purple. It's really cool. And that's due to the nitrogen content. And then our exoplanet experiments are like more blue in color because of oxygen. So that's always fun. It might be a video. It's not a video, just kidding. Anyway, after a few days of letting these gases react with the radiation, solid particles start to build up along the walls and the bottom of the chamber. These are our haze analogs. So we scrape the sides of the chamber and collect these samples to do analysis on or use in future experiments. So my future experiments were hydrolysis. So I just dunked them in some water in these little vials and let them to sit for 3 weeks. And after those 3 weeks, you can see an appreciable color difference, which was a good sign to us that chemical reactions were indeed happening. And then I will also note that we had to separate the soluble and insoluble components of this sample for our different analysis techniques. This whole experiment was a bit proof of concept because nobody has taken these types of measurements of hydrolyzed samples before. So, bit work in progress. It was fun to figure out the methodology, but yeah, this is what we had to do, is analyze them separately. Sweet, okay. So the results we are looking at today are called transmittance spectra. They were taken by a Fourier transform infrared spectrometer. And in this plot, we're going to be looking at wave number on the bottom x-axis and wavelength on the top x-axis. I'm sure, hopefully, you're familiar with at least one of these two things. They both are measures of light, essentially. But wave numbers are typically used by chemists and wavelengths used by astronomers. So I do have to be very careful to include both on every single plot. Transmittance on the y-axis means that a transmittance of 1 means that all light makes it through your sample, while a transmittance of 0 means that no light makes it through because it's all being either absorbed or scattered by your sample. The brown line is going to be the insoluble component of our hydrolyzed sample, while the orange is your soluble component. We also have this white or gray line, which is the original unhydrolyzed sample spectra for comparison. We took spectra from 0.4 to 28.5 microns. This covers all of the JWST range and most of Hubble's range as well. But for today, we're going to focus on this small well, it's not that small, it's a log scale, small infrared region of the spectra because that's where most interesting things are happening. So experimentalists care about this because functional groups show up here, but astronomers like it because a lot of molecules absorb in this region. And those absorptions create almost like a fingerprint of the atmosphere they're looking at. Cool, so let's start with Titan. In the upper left, we have our full spectrum, while our mid-infrared is front and center here. For time, I can't go into all the changes that we see after hydrolysis. What's happening here? So I'm going to just start with a few that I think are most interesting. So for our Titan samples, the most interesting thing that happened was oxygen incorporation. Our original Titan synthesis has no oxygen in it, right? It's just photolysis of nitrogen and methane. So these peaks, it's that little guy right there and that little guy right there. Those are new peaks in our hydrolyzed samples that weren't there before, and those correspond to CO stretching. So that's really big news. I think that this has major implications for habitability on Titan because it opens up a whole new range of possible prebiotic pathways. Okay, cool. Exoplanets, our 300 Kelvin water-rich exoplanet sample. The exoplanets do have water in their original synthesis, so we're not looking for incorporation as much as just shifts in the bonding structure. And we do see those here highlighted in purple, green, and yellow. So the purple region is going to represent different OH stretches that are changing somehow, and I think they correspond to these green and yellow regions that are responsible for nitriles, isocyanates, and amides. We're particularly interested in the green region because that's where a lot of amino acids show up. So I'm very curious to characterize these samples further and understand where that's really coming from. We unfortunately can't get that from transmittance spectra, but stay tuned, we're excited. And lastly, our 400 Kelvin water-rich exoplanet. You'll see right away that there's no orange line. That is because we did not collect enough soluble sample to analyze. It's interesting because the spectra look broadly similar to the 300 Kelvin exoplanet, but there must be some difference in production rates due to different chemistry that's happening. So I will be running these experiments again this summer with some updated methodologies, and we're hoping to get production rates as well to maybe tease out why the 300 and 400 Kelvin planets are producing different chemistry. Cool, so as I mentioned, these transmittance spectra don't actually give us really detailed composition measurements. Instead, the goal of these measurements was to use them in deriving optical constants. Optical constants are wavelength-dependent values that describe a material's absorption and scattering. So they define that fingerprint that I was telling you about earlier. Modelers and observers use these to produce their synthetic spectra. So ideally, these people would have access to huge databases of optical constants just filled with every molecule that they could possibly see in their atmosphere. So they can mix and match these optical constants until they match the spectra that they see in real observations. We would like to add hydrolyzed hazes to these types of databases. So if there's any modelers out there, hit me up. Yeah, it would be awesome to see hydrolyzed haze in a real atmosphere. For next steps, based on the spectra, we do think you could see the changes from hydrolyzing the samples before and after in real spectra, but we'd like to produce our own models to show that for sure. So that's a good next step. But then the main thing I'm interested in is this mass spectrometry measurement, because that's going to give us detailed composition analysis of what amino acids, what nucleobases are being created and destroyed. So stay tuned for that. Hopefully I'll be doing that within the next year or so. Sweet. So I'll just say a quick thank you to the Hearst group at Johns Hopkins, particularly my advisor Sarah, Chao He for teaching me everything about the lab, Sarah Moran for giving me samples and life advice, and of course everyone at Hopkins and my friends and family. I will leave up a summary slide and take questions.
Hey, Mike Wong from Carnegie Science. Wonderful talk, great results. I always enjoy seeing Phaser Lab things. I was wondering, when you take the haze product from the Phaser Lab and transfer it into the vial for the hydrolysis, do you keep that anoxic, or is there oxygen in the headspace of that tube?
That's a great question. So we collect all of our samples in a nitrogen glove box, and that's typically how we store them. for these experiments, a bit for simplicity, but also because we knew that these were sort of preliminary, we did take the samples out of the glove box to do the hydrolysis. We didn't want to put water into the glove box, and right now we don't have like another one to contaminate. But we figured, well, we're going to be putting them in water anyway. What's like Earth's atmosphere going to do worse than what we're already doing with the water? Maybe that's not the best approach, but since these were preliminary, we ran with it, and I would love to hear any experimentalists' suggestions for how to make that better.
Cool, thank you.
Oh, sorry.
Hi, Jin Wang from University of Arizona. Thanks for the very interesting talk. I'm just wondering, when you simulate the production of the haze in the chamber, will it be slightly different when you consider the transport on Titan, like both horizontal and vertical transport?
That's a great question. So since this is all happening in the upper atmosphere of the planet, like most of this UV is happening way up high before it gets absorbed by other things, our pressures in the chamber are really low. It's on the order of a few millibar. So I don't think we have to worry so much about like the intense winds that are on Titan. But the gas is getting continuously flowed through. So there's no like stagnant gas in there.
One more.
So great talk. I loved it. I also do stuff on Titan, so I love, and I've actually cited your advisor in a paper before. So I know you mentioned that under Titan's surface with possible like liquid water, if there was like, a comet or some type of like destruction could come out and like be on the surface. Wouldn't that necessarily just exist then as a solid, just because of how outside the habitable zone Titan is from liquid water existing? And would it have to be warmer for that to happen? And then also, sorry, another thing about your methane, because love methane too, but since methane exists really small and it's like a irreversible destruction, do you think that potentially there won't be any, this is just more purely, sorry, but like later on, methane can't be, reproduced and stuff like that. So do you think that would impact these, organic molecules in the atmosphere?
Yeah, great question. I'm gonna answer the second one first while it's fresh in my mind. So yeah, the whole like methane story on Titan is not super well known. It's obviously very effectively destroyed, but we don't know what the replenishment mechanism is. I would love to find out, and that's definitely, if we ran out of methane, we'd stop getting haze, and that would be weird, really weird implications for Titan. But yeah, I just say that's an open question in the field still. And the first one was? Yes, right. Yeah, so we're really basing that off of a set of like models that had been done that showed, I don't remember like the impactor size right now, but for a certain impactor size, the impact generates enough heat to keep liquid water stable for a long time. And hundreds of thousands of years is not a long time like geologically or anything, but it's plenty of time for these types of reactions to occur. So, there's also plenty of work should be done if you took the sample out earlier, like if the water was there for a lot less time, but, that's all future experiments. Cool. Thanks. Sweet. That's it. Thanks, guys.
All right, our second speaker in this section is going to be Paula Cunha, speaking about simulation of potentially habitable environments on the surface of exoplanets.
Okay. Okay. There is a laser.
Yes.
Okay, thank you. So, hello everyone. Can you hear me out? Okay, nice. So I'm Paula Cunha. I'm a master's student in astronomy at the Valongo Observatory in Brazil. And my advisor is Luan Gezi, and here you can see our collaborators. And to summarize, my research is about potentially habitable environments on the surface of exoplanets. But what are those potentially habitable environments? Okay, here I have this list of potentially habitable worlds. Last year it was potentially habitable exoplanets. They changed it this year. And in this list, you can see exoplanets, most likely to have a rocky composition. And also they are in the habitable zone of each star. But what is the habitable zone? Is the distance of the planet from each star, where it's possible to have liquid water on the surface of these planets. Okay, so pay attention for this first one, Proxima Centauri b. It orbits the closest star of our solar system. It has around 11 to 12% of larger than the Earth mass. It was discovered by radial velocity method of detection in 2016. And it was confirmed recently in 2020 by Suarez Mascarenhas. All of those exoplanets here were found around M dwarfs because of the limits of our detection methods. Except of those two ones that I highlighted here, they were not found around M dwarfs, so ignore them. But what are M dwarfs? M dwarfs are low mass stars, around 0.08 to 0.55 solar masses. Here in this peak, you can see a comparison, the size of Proxima b and, for example, Jupiter and our sun. M dwarfs comprise around 70 to 75% of our solar neighborhood, and they are interesting to study exoplanets, as you can see in the potentially habitable worlds list. However, M dwarfs can be very challenging because of its flash can be frequently and intense. In a flare event, the star realizes a large amount of radiation, including UV radiation. And UV can be important for life, for example, the vitamin D production in the human body. But excessive exposure can lead cells to oxidative stress and nucleic acid damage. So considering all those features of M dwarfs, remember, interesting to study exoplanets, however, challenging environments of radiation and flares, we can make the questions. Can life survive on these conditions? So to try to provide data to try to answer this question, we perform experiments at the lab with extreme conditions considering UV radiation and gas compositions. We performed our experiments with microorganisms and then compare with the Proxima b surface. Okay, first, we have to choose our microorganisms. We used yeast, Hydrothermal dynense. It was collected in Brazil, Diamantina. Our group have been studying Diamantina because it's an interesting place with interesting features that can be analogous to the Mars environment. For example, the high solar incidence of radiation and the presence of iron oxides in the soil. And we call it D23 because it's from the 23 collection site. Okay, but what about our irradiation experiments? We used two light sources. The first one was a UVC tubular lamp where it has this peak in 254 nanometers in the UVC range. And the second one was a UV continuous spectral lamp. This lamp covers the entire UV range. So just remember, we can split the UV range in UVA, UVB, UVC. Here you can see the wavelengths. So again, the UVC lamp is only for the UVC, and the UV covers all those three, UVA, UVB, and UVC. Okay, so our yeast, we irradiated in saline solution, and also desiccated yeast. In the nature, you can find desiccated yeast where the yeast is not in the presence of water and that it has a low metabolic activity. And thirdly, we use the Astrobiology. Astrobiology means space and planetary simulation chamber, where you can change the pressure, the temperature, the gas composition, the light source. So I think you guys are used to it because of the past lecture. Okay, about the atmosphere of Proxima b, we don't know the composition yet. Also, we don't know if these planets can hold an atmosphere. So we have to make our guesses. We used two interesting compositions for astrobiology. The first one was 100% of CO2, which is an extreme scenario case for CO2, and also it's close to the Mars atmosphere at 95% of CO2. And also a possible composition for the primitive Earth of 80% of CO2 and 20% of N2. We keep the pressure of the Earth, and we use the continuous spectral lamp, and our yeast was desiccated in this experiment. Okay, so just to summarize, we performed 6 kinds of experiments. The first group of experiments was in saline solution, used the UVC lamp and continuous spectral lamp. And the second group was our yeast desiccated with the UVC lamp, continuous spectral lamp, Astrochem, 100% of CO2, and Astrochem primitive Earth, 80% of CO2 and 20% of N2. Okay, after our experiments, we count the colony from units, where we count the colony of viable cells, and our experiments were performing triplicates. Okay, so let's see our results. So for the axis, the y-axis, I have the viability n per n0. N0 is our control samples. It was kept in the dark all the time. And n is the irradiated samples. For the x-axis, we have the fluence value, joules per meter square. Okay, and at the top here, we have the desiccated for the continuous spectral lamp in green and UVC lamp in blue, the X. And here at the bottom, we have the orange for the UVC lamp in saline solution and purple for the continuous spectral lamp in saline solution. So as you can see, we have a steep decreasing for our saline solution curves, and the desiccated curves keep almost constantly. Actually, we are expecting these results because of the low metabolic activity in desiccated cells. So it can do better with the radiation damage. Okay, now for the desiccated experiments, but for high values of fluence. Again, the blue one is the UVC lamp, and the green one is continuous spectral lamp. So here, for the continuous spectral lamp, you can see counting of viable cells until 10,000 joules per meter square of fluence. And for our UVC lamp, we have counted to 60,000 value of fluence. And also you can see a steep decreasing as well for the continuous spectral lamp compared to the UVC lamp. A possible explanation for this is because the UVA, UVB, and UVC range are responsible for different kinds of damage. The UVA and UVB are more for reactive oxygen species, and UVC is more for the products. So here, in our continuous spectral lamps, the cells are dealing with these two kinds of damage. For Astrochem now and our atmospheric compositions, again, the same axis, we have the continuous spectral lamp again, and we have the pink and diamond one for 100% of CO2, and we have the yellow gold circle one for the primitive Earth. So you can see that 100% of CO2 is very close to the continuous spectral lamp, but there is a difference between the 100% of CO2 and primitive Earth. We are not expecting that, so we want to perform more experiments to investigate this difference. Okay, now about the flux of flares of our star, Proxima Centauri. To obtain a spectrum of the star is very challenging, especially UV, flare, and for AbGradCon. Remember that we don't have UVC in the surface of Earth. UVC do not reach the surface of Earth. And also AbGradCon has that peak in the infrared. So it's about modeling. But we found this work of Fletch, 2007, who analyzed the flares of 52 M dwarfs. He observed these stars in the galaxy evolution explorer in the UV and UV bands. Here you can see it's very close to the UVC. And after some math, we calculated an average value of 7 watts per meter square at the distance of Proxima b, which is 0.0485. AbGradCon 2020 also used this value for average value of flares. So, okay, again, our results for the desiccated East with UVC lamp and continuous spectral lamp. If we calculated the time, remember that we have counted to 2,000, 10,000, and 6,000, okay? So calculating the values to the hour to reach these values on the surface of Proxima b, remember the 7 watts per meter square, we can find that to 6,000 for the UVC lamp, it can resist to a flare of 2 hours and 2 hours and a half. And for an extreme scenario case, that the continuous spectral lamp, you'd have a survival to a flare of 24 minutes about. So to our future at perspective, we want to do the same analysis for other exoplanets and extremophiles. We also want to perform more experiments with AstroCam. And with this work, we want to provide valuable information for the future analysis of biosignatures for this generation of telescopes and facilities. And my message is we perform irradiation experiments with the UVC lamp, UV lamp, and AstroCam. Our yeast, Hydrothermal Lunine, showed interesting microorganisms to study the radiation resistance, and the potential of Brazil and Diamantina to search for extremophiles or study analog environments. And also, the Proxima b environment can be challenging for life as we know, because, okay, it can survive to a flare event of 2 hours or maybe some minutes, but if you consider multiple flares per day or per month, maybe it can be challenging for life. So that's it. Thank you.
Thank you so much for the talk. I had a question. What was exactly the protocol for drying the cells?
Okay. Let me show you the pic again. So here we use this is the Teflon to make the cells easier to remove it and to count after our irradiation experiments. We diluted the cells in distilled water. And then I made some drops here in the Teflon and let it dry to make sure the water was evaporated. So it's dry cells here.
Okay. No, I just wanted to see that you didn't dry them with a saline solution. So that's great.
Okay.
Hey, great talk. Hello? Yeah. I was wondering if you've thought about like future experiments with other bacteria or other types of stars and how you think that might affect your results?
Yeah, I'm thinking about to do the same analysis for other exoplanets. I'm very interested in M-dwarfs and the environments of M-dwarfs, and they can be very challenged in these aspects of radiation. And also, if a planet can, like Earth, can hold an atmosphere, so I'm very excited for the next decades of results from JWST and so on. So, for the future, okay, I would see if there is an atmosphere or not. Okay, so it would be a difference, the atmosphere to protect the life. And also the aspects of how much the amount of UV radiation reach the surface. So I expect this, the time of the flare events can be shorter or tiny, depending of the radiation that the star realize.
That's cool, thank you.
Yeah, if you
talk about Jay from University of Arizona. So I was just wondering, how do you determine the viability of desiccated yeast? Do you regrow them and count the CFU, or how do you measure the viability of desiccated yeast?
Okay. Okay, so the yeast are here. So I put them again in a saline solution, and then I do all the dilutions, serious dilutions, and then I put it in plates like that, 3 drops, and every drop there is a community of colonies of viable cells. So it's here we have 2 drops, right, for every dilution, and every drop has a group of colony forming units. So I count this colony. So here you have some amount of viable cells. So it's how I made my curves.
Testing. Okay. Hello. So hi, everyone. My name is Cindy Liu. I'm a graduate student at the University of Texas at San Antonio. Just finished my first year. So my topic will be, can the presence of a supercritical ocean explain the atmospheric composition of K2-18b? I don't think I got the pointer. I'm so sorry. Okay. So what is K2-18b? It's a type of exoplanet called a sub-Neptune, so it just means it's between the size of Earth and Neptune. And we don't really know what their structures are like. We don't know if they're more Earth-like, so more terrestrial, maybe rocky, maybe habitable, or more like Neptune, so more gaseous with these deep envelopes, or something in between. But these exoplanets, they make up the majority of confirmed exoplanets, so we really want to be able to characterize them to see, how many of these are more Earth-like, and what are most of these exoplanets like? So a lot of different structures have been considered for this exoplanet. So first, we have a mini Neptune, so like a smaller version of Neptune. Second is a rocky world, so that's a super Earth with a terrestrial surface. Maybe a liquid ocean world, a magma ocean world, or a supercritical ocean world. So these are very, very different structures with a lot of different implications for habitability and interior processes. So
How do we narrow down which one is the most plausible? We have to look at its atmosphere. So this was from, sorry, I don't have it cited here, but Madhusudan 2023. So the transmission spectroscopy revealed the first detection of methane and CO2 in this type of exoplanet ever. And that's exciting because for some reason there's this missing methane problem where we see methane in a lot of solar system atmospheres, but we're not finding them a whole lot in exoplanet atmospheres. So finally, we found methane out there somewhere. And there was also a non-detection of ammonia, carbon monoxide, and water. And so this paper said that these results are consistent with a Haitian world. That would be a temperate global liquid ocean world that has a hydrogen-dominated atmosphere. And they also said they have potential evidence of dimethyl sulfide. That would be a biomarker as it is produced by algae and phytoplankton here on Earth. But of course, to really know what's the most plausible structure, we have to check against all those other models before we say for sure that's going to be a Haitian world. So we've tested a lot of them already. Not we, but like other K218b people. So the deep atmosphere, no surface case, shallow atmosphere with a rocky surface, shallow atmosphere with a liquid ocean, and then a deep atmosphere with a magma ocean have already been tested. The supercritical ocean case hasn't really been tested yet, but that's what we're going to talk about in this presentation. So before I get into that, I want to talk about the results from the previous modeling efforts. So first, the deep atmosphere case. So we're looking at a mini Neptune, not really a tangible surface. We have a layer where clouds are condensing with water. And so this can explain the absence of water in the atmosphere. It does explain the methane and CO2 abundances through deep atmospheric quenching. But for some reason, it predicts quite a bit of ammonia and CO compared to the non-detection and the observations. So it can't perfectly explain the observations yet. Now for the Haitian world cases, there are two subcategories explored here. So first we have a lifeless Haitian world, a liquid ocean. There's nothing in there, unfortunately. So no life yet, but this does not have nearly enough methane to explain the observations. It'd be destroyed through photolysis and oxidizing reactions, and so doesn't really match the observations. We don't really see this in the race anymore. Now for an inhabited Haitian world, the inhabitants are considered to be some kind of Archean microbes, right? So this can explain the abundances of methane and CO2, but there has to be methane coming from the ocean, perhaps from these microbes. But the thing about a liquid ocean world is that it has to have a very thin hydrogen atmosphere to make sense with the mass and radius constraints. But this exoplanet is very, very close to its host star, about 0.15 AU away, so closer than Mercury. And since it's so close and the atmosphere would be so thin, that atmosphere would be stripped away from the extreme ultraviolet radiation. So something would have to be replenishing the hydrogen. We know that volcanoes replenish hydrogen, but we don't really expect volcanoes here. So there has to be something else replenishing the hydrogen. Lastly, it's also expected to experience a steam runaway greenhouse. A hydrogen-dominated atmosphere will have a lot of collision-induced absorption. This drives up the surface temperature, and it enters that runaway greenhouse state a lot quicker than, say, a nitrogen-dominated atmosphere like Earth. So we have a very, very unstable climate here, and we need a lot more explanations to really see if this is a feasible scenario. Now, the rocky planet case, well, we're not even looking at that anymore. It's not even possible. So it would be way too dense to match the mass and the radius. It would have to have a very, very thick atmosphere of at least 1,000 bars. So it wouldn't even be a super Earth anymore. It'd have to be like a mini Neptune. But yeah, this one's out of the race, unfortunately. Now the magma ocean case, this would be a mini Neptune that has a silicate magma melt at the bottom. So this could explain the non-detection of ammonia and of water. The nitrogen would be very soluble in the silicate melt. So it would stay in that layer of magma instead of entering the upper atmosphere. But it also predicts, Oh no, it's not layered. Okay, that's okay. It predicts a lot of carbon monoxide as well, along with the CO2. And so, again, given the non-detection, we still need an explanation for that. So now, the supercritical ocean case. Thinking back to that liquid ocean case where it was very unstable, we would need that deeper atmosphere to maintain the atmosphere, and we had that super runaway greenhouse state. So all those factors together will drive a surface ocean to become supercritical. And if it were supercritical, it would be what we call a stratified mini Neptune. So like a smaller version of Neptune, but it has a layer of supercritical hydrogen and water that are mixing together, a layer of clouds where water is condensing, and then a hydrogen-dominated atmosphere where we have some traces of helium. But why haven't we done this before? Well, as you can see, there's no clear boundary between the ocean and the atmosphere. Unlike a liquid ocean and a regular atmosphere, they're mixing together. So that makes things a bit more difficult. Photochemical models don't account for interactions between a hydrogen atmosphere and a supercritical water layer. So instead of photochemical models, we adapt with geochemical models. And we want to explore the geochemistry of a possible supercritical ocean. We model an ocean in equilibrium, as we expect that a supercritical ocean would have very high temperatures, enough to be in equilibrium. And then we model the ratios of methane to CO2 and CO to CO2 in both the liquid and the gas phases, and we want to see if that gaseous speciation is going to match the observations at all. So first, we begin with the RevProp database. We just plot the saturation boundary of water. Here's a phase diagram where we have an inverted y-axis. So as we ascend, it's basically like ascending in the atmosphere, and the bottom kind of represents the surface. Then we use the aqua equation of state. We generate pressure-temperature profiles at surface pressures of 1 kilobar, 2 kilobar, and 3 kilobar. Then at surface temperatures between 100 degrees Celsius and 1,000 degrees Celsius at every degree. So technically, there's like 900 profiles here, but we just showed 10 of them. Then we use the deep earth water model to get the equilibrium constants and Henry's law constants, which will tell us about the speciation. So here, the red stars represent where we do the aqueous calculations, and then the red circles represent where we do the gaseous calculations. And if we take a closer look at this phase diagram, there's actually two scenarios represented here. So if we're looking at these profiles that go in the liquid phase and then intersect the boundary, that represents a liquid water ocean interface. So just your typical liquid ocean, atmosphere on top, we can easily do the calculations at that interface. If we're looking at the profiles that go from the supercritical phase, then vapor, then intersects the boundary then represents a cloud layer. And we have to do this, of course, because there's no boundary between the atmosphere and the ocean. So the next location we can do the calculations are at the cloud interface, where the cloud represents another liquid region. We also need to know the hydrogen concentration to do the calculations. So from mass radius constraints, formation modeling, interior modeling, we have two end-member cases for the inventory of hydrogen and water. So the first one says we have 0.02% of hydrogen and helium, 50% water, then 2% of hydrogen and helium, and 18% water. This gives us a pretty big range, I might say, of about 0.15 to 42 moles of hydrogen per kilogram of water for the concentration. We are working on constraining that a little bit more, but so far that's what we got. So first with the aqueous speciation. So each set of colors that represents the 1 kilobar, 2 kilobar, then 3 kilobar curves respectively. And that black dashed line represents the observed ratio from the transmission spectroscopy. So there's the aqueous speciation, and then we have the gaseous speciation. So they're not very different, and that's what we expect. We look at the gaseous speciation to compare with the atmospheric observations. Oh, it's kind of hard to see the range of error here. There is a sort of gray region around the black dashed line. But that gives a temperature range of about 715 to 1165 Kelvin to match our observations. We then do the CO to CO2 speciation. So instead of using hydrogen as a parameter here, this is instead set by the observed CH4 to CO2 ratio, because it's a lot better constrained. As you can see, oh, well, you can't see, but below that black dashed line, everything below that is the region of error. So that's pretty big, but at the very least, it gives us an upper temperature limit of about less than 973 Kelvin to match our observations. So putting them together, we have a little happy supercritical water world here. It's still in the running. So putting them together, we have a temperature range of about 715 to 973 Kelvin. Critical point of water is at 646 Kelvin, so this tells us that a supercritical ocean is indeed possible on K2-18b. Is it still habitable? Well, that's like 500 degrees Celsius. So at least from what we know right now here on Earth, it's unlikely to have life at least familiar to Earth. It could have some kind of weird other life that we don't know about, but as far as we know, probably not habitable. But it's still a very exotic environment to explore. I mean, a global supercritical water ocean. So how does that fit in with all the other models? Well, first we look at the methane and CO2 speciation. If it's somehow so much less than what the observations say, maybe we can have that super Earth with a liquid ocean with no life in it. But of course, we have a lot more scenarios that do match the observation, so then we ask, is there carbon monoxide? And if not, then that describes our supercritical water ocean case here. If yes, we gotta ask, is there ammonia? And then if yes, maybe it's the mini Neptune. If not, maybe we had that silicate magma ocean or that super Earth that does have a liquid ocean with some kind of methane coming from the ocean. So there's a lot of work still to be done to really see what this planet is like. What's the work that we're gonna do? We will have to model the nitrogen speciation. The reason why we didn't do it here is because we don't know a lot of additional variables such as the pH of the ocean. Low pH will have a lot more ammonia production. High pH will have a lot more ammonium production, so we'll have to consider that. We also don't know how much nitrogen there is. I mean, atmospheric nitrogen doesn't show up in the infrared, so we have to find some way to quantify how much there is. And lastly, ammonia is a lot more soluble than those carbon species. So it's expected to condense in that cloud layer. And we'll have to figure out some way of, how much is condensing. But lots of exciting work. And I'll leave you with my conclusion. So a cold liquid water ocean is inconsistent with my equilibrium calculations, not mine, sorry, our. And a supercritical water ocean is instead possible between this temperature range. I'm not saying that it is for sure a supercritical water ocean, but it's definitely something that's still in the running that we still need to consider. And hopefully, in the future, we'll get a much better constrained CO mixing ratio to really minimize that region of error. Thank you so much for listening.
Hey, Cindy.
Hi.
Thanks for the fabulous talk and all this great work. I was wondering what your interpretation of the dimethyl sulfide detection is based on your geochemical modeling, assuming that it's actually there.
My interpretation. Let's see. I don't have much confidence in the dimethyl sulfide. Let's see if I can go back to that figure. I believe in the transmission spectroscopy, a bunch of biomarkers were tested, and they kind of just see which ones match the best. But the paper kind of cites a lot of marginal evidence, potential evidence, and I think in general, I personally feel like it's probably not there. I, of course, could be wrong, but I think there's a lot of other papers suggesting it's probably not there. Maybe who knows? Yeah.
Cool. Thank you.
Hi, I'm Veronica Hegeline from Cornell. Are there future JWST observations planned, and how is that going to help you further refine your testing of the different models?
Yeah, so there are future observations planned, and I think mainly we're really hoping it constrains that ammonia mixing ratio and carbon monoxide mixing ratio, because I mean the difference between a lot of these structures, sorry, let me go back to that flow chart, depends on whether or not it's actually there, but maybe there's just low levels and it hasn't been detected yet. So it will definitely make a huge difference in deciding which one of these will be a lot more narrow, and yeah, we'll definitely have to refine our models to see if it can match those constrained observations.
Thank you.
All right, thank you. While Austin's getting settled, I will introduce him. So Austin Ware is going to talk about continuous habitable zone predictions for habitable worlds observatory target stars.
Okay. Can you hear me? Okay. No.
Just move this along.
All right, yeah. Hi, everyone. I'm Austin Ware, sixth-year graduate student at ASU. So talking about continuous habitable zones for Habitable Worlds Observatory. All right, so first I guess I'll just kind of describe what Habitable Worlds Observatory is, or HWO. So here you can see the LUVOIR-A concept design. So LUVOIR and HABEX were mission concepts that kind of inspired what HWO will be. So not an actual image of HWO. We don't know what it's going to look like yet, but maybe something like this. And so this will be NASA's next flagship astrophysics mission after the Roman Space Telescope. It's going to be a 6-meter class UV, optical, and infrared direct imaging telescope with a coronagraph. So it'll block out the light from the star with the coronagraph, and then hopefully be able to see the planets around it. And so it'll have a goal of surveying habitable zones of around 100 sun-like stars. So these are F, G, and K spectral type stars. And then hopefully spectroscopically characterize the atmospheres of 25 rocky habitable zone planets. And so just to give you an idea of the massive observational and literal costs that will be associated with each planet, for the HABEX and LUVOIR reports, they set an upper limit on the integration time for observations of 60 days. So it's going to be sitting there and staring at one planet for potentially months at a time. So just a massive cost just to be able to maybe characterize the atmospheres of one planet. So here's just a summary or overview of kind of a preliminary target list for HWO. So this comes from the Exoplanet Exploration Program mission star list. And so there's a total sample of 164 stars. As you can see, mostly F, G, and K stars. There were like 3 M stars that did fit their criteria, though. And then separated into 3 different tiers, where tier A stars will be the most accessible, have the most accessible habitable zones for this 6-meter class telescope. And then progressively worse as you go down into here, or requiring better technology. Yeah, and so this current prioritization is based off of the Casting et al. 1993 habitable zone limits, kind of like the first habitable zone limits for the sun, and then those are scaled by the host star's luminosity for non-solar targets. And so importantly, and I'll get into this in a second here, this prioritization does not consider how the habitable zone depends on the effective temperature of the host star, and also does not consider the age of the star. All right, so yeah, we have a large sample of stars and hopefully planets, and a just ridiculously high observational cost per target. And so if our hope is to detect life on these planets, we want to prioritize those systems or planets by those most likely to host detectable life. And so to do that, I'll be talking about continuous habitable zones. But first, I should probably define what I mean when I say habitable zone here. So I'm always going to be talking about the circumstellar liquid water habitable zone. So assuming an Earth-like planet, so rocky with sufficient atmosphere, if it's in a certain range of installation, it could have liquid water on its surface. But we often think of the habitable zone as this static thing that just exists around any given star, but it's not static. It's going to evolve over time as the star evolves, and the planet too. In my analysis, I consider the continuous habitable zone. So here we have a plot of the habitable zone radius on the y-axis versus time, and we see as the star evolves, the habitable zone moves progressively outward as the star gets brighter. So we can define the continuous habitable zone as the orbital area remaining continuously within the habitable zone for some length of time. But how long in the habitable zone is long enough is really the important question. So as with most things, we can look to the Earth for answers about this. So we have atmospheric O2 versus billions of years ago. And around 2 billion years after the formation of Earth, or 2.5 billion years ago, the great oxidation event occurred, where photosynthetic organisms produced a significant amount of oxygen and potentially produced a detectable signature in Earth's atmosphere. And so if you were just interested in maybe like detecting disequilibrium chemistry in an atmosphere, you could probably go to an earlier time than this. But this kind of gives a conservative length of time for how long a planet should be in the habitable zone in order for life to arise and then make a detectable impact on the atmosphere. So we can define the 2 gigayear continuous habitable zone, or the CHZ2, as I'll refer to it from here, as the orbital area remaining continuously within the habitable zone for 2 billion years or longer. But so in my analysis, what habitable zone models am I actually using? So here we have stellar effective temperature and the effective flux incident on the planet relative to Earth. And the red and green lines correspond to the moist greenhouse and maximum greenhouse habitable zone boundaries from Kaparapu et al. 2013. So these are two of the most commonly used inner and outer edge boundaries, and are the most similar to those used in the HABEX, LUVOIR, and HWO emission star list. But crucially, these are defined with respect to the effective temperature of the star. And we can see that they relatively move outward as you go to lower effective temperatures. But then the third line here, the blue line, is from Turbay et al. 2023, and this defines the water condensation limit. And this functions as the initial inner habitable zone boundary. So once the star enters onto the main sequence, this defines that initial habitable zone boundary. If a planet, once its host star is on the main sequence, is interior to this line, the blue line, it will not be able to have water condense onto its surface. So after that initial magma ocean cools, the water will be in the atmosphere. And if it's interior to this, there's just too much incident flux to be able to have the water condense. And so it will stay in the atmosphere until it is slowly lost to space over time. But if at the beginning of the main sequence, the planet is outside of this line, then the water will rain down onto the surface and be able to form oceans. And so I also have plotted here modern Earth and early Earth and modern Venus and early Venus. And we can see, even though modern Earth is interior to that blue line now, early Earth, when the sun was dimmer, was outside of that line. And so, of course, we have oceans. But Venus was never outside of that water condensation limit. And so if these results are to be believed, that means that Venus was never able to form oceans on its surface. And so this is really important to include when doing any type of habitable zone analysis, because it basically tells you which planets can and cannot form oceans on their surfaces. And so I combine these habitable zone models with Tycho stellar evolution models to model the habitable zone over time. And this is inside of a Bayesian framework that I use to then predict the probability that any given radius around a star is within the CHC2. So just kind of a simple description of what this model does. So we take the prior probability that the orbital radius is in the CHC2. So this is based off of the stellar evolution models, combined with the habitable zone models. And then we have the likelihood of the models given the measured stellar mass, metallicity, or composition, and age. And so essentially just multiplying the prior and the likelihood together, we then get our posterior likelihood, which is the probability that any given radius is in the CHC2. So what does this look like for the sun? So here we have probability of any radius being in the CHC2 on the y-axis, and then the distance from the star. And also plotted here, we have the orbital radii of Venus, Earth, and Mars. And so here I'm not considering the age of the sun, so assuming we don't know the age. So it can have any age between the beginning of the main sequence and the end. And kind of get this like Gaussian distribution for the probability. And we can see here that this would predict that Mars actually has a higher probability of being in the CHC2 than Earth. And this is just because, based on these habitable zone definitions, over the full main sequence lifetime, Mars would spend more time in the habitable zone than Earth. But once we consider the age of the sun, which you know really well, which you know it better than this, I just use an astrophysical estimate of the sun's age. It's more relevant for what I'm doing. But yeah, so we know it really well. And so it goes from being kind of this like weird looking Gaussian to basically just a top hat function, because we know the mass, the composition, and the age exactly for the sun. Once we consider the age, then we can see that Earth is given 100% probability of being in the CHC2 as expected. And Mars is too, but that's for other reasons unrelated to the star. All right, but so for exoplanets and for their host stars, we don't know the mass, composition, and age exactly. And for the age in particular, we maybe have a rough idea of it, but in most cases, it's fairly uncertain. And so taking into account those other uncertainties, we get more of a Gaussian distribution for exoplanet host stars. And so these are two stars that are in the HWO sample. So for the one on the left here, Kappa 1 Ceti, G5 star, has a relatively young age, about 1.25 billion years, based off of my estimates. So that would give it a maximum probability of around 40% that a radius is in the CHC2. And really, if that age was more certain, it would have a 0% probability, because it's not even 2 billion years old. And then for Chara, G0 star has a mean age above that 2 billion year mark, so has a much higher maximum probability of around 90%. So we can see how much the age influences these distributions and is really critical for this work. But yeah, so how do we take these distributions then and turn them into a usable number that we can then use to like rank a system or a planet? So if we knew planets in these systems, we could just say, oh, it's at this orbital radius, so it has this probability. But for the HWO sample, we actually don't know. We haven't discovered any habitable zone terrestrial planets around these stars yet. So what we can do, so first I should discuss just quickly the inner working angle. So when you're using a coronagraph, obviously you cannot see anything inside, interior to the edge of the coronagraph. So you have an inner working angle that defines where you can see inside that system. And so if we were to just say the inner working angle is about here, so taking into account how far the star is from us, what we can do is integrate over this probability distribution outside of that inner working angle and kind of come up with then an effective CHC2 range to compare between different stars. And so actually for these two stars, these are two of the best in the HWO sample. The full habitable zone will be visible even with the most conservative estimates of what the inner working angle will be. So yeah, as you can see, the CHC2 completely lies outside of the inner working angle here. So if we do this integration over the probability distributions, we can then see that Chara has a much higher effective CHC2 range than Kappa 1 SETI does, mostly just based off of the age here. And so we could use those to then rank them and say, you know, Chara is probably a better candidate to spend more time looking at than Kappa 1 SETI is. All right. Yeah, and then just kind of summary and next steps here. So using these CHC2 probabilities, we can further prioritize observations by considering those planets or stars that are most likely to host detectable life. And so for both my work and for just studies of habitability, comparative planetology, or just in general, accurate and precise ages are critical and is really one of the areas that we are most lacking in astrophysics right now. Because if you don't know the age, you really just can't put anything you're observing into context. Yeah, so this is still currently a work in progress. I've done these estimates for all of the main sequence, so dwarf stars that are in the HWO sample, but I'm currently expanding our stellar evolution catalog to be able to include those more evolved phases. So we can include the subgiants that are in the sample. And so I'll publish the results for the full 164-star list, along with estimates of the mass and age for all of those stars. Yeah. All right, and yeah, I'll leave this up and take questions. Thank you.
Hi, this is Hypatia Medavia from ASU. This is a totally naive question because I just do like little baby solar system objects. What causes so much like uncertainty in the ages of the stars? Like what makes those measurements so difficult?
Yeah, so for my estimates, I am just using my stellar evolution models to fit the measured properties. So obviously there's the associated uncertainties in the mass and composition of the stars. And also, I'm just using 1D models. So there's only so accurate that a 1D stellar evolution model can be. If you wanted to be really accurate, you could use 3D models, but that would take forever to run for even one model for a single star. And so there's just a lot of uncertainty in the evolution models due to simplifications in the physics. And there's also a very limited number of independent methods for measuring ages. So you can do it based off of gyrochronology. So basically you measure how fast the star is spinning over time it will spin down due to magnetic braking. And so that can give you an estimate, but that really only works for young stars. If it's in a cluster, you can get much better estimates because you can kind of do this like fitting to isochrones, but you can do it for a huge number of stars and get a much better estimate of what the age is. But that also mostly just works for young stars. So really the problem is that we don't have a lot of great ways to measure ages precisely for older stars. Yeah.
Cool, thank you, that was great.
Hi, really interesting talk. I'm Ben Vegas from here at Cornell. My question relates to your kind of the setup of your prior using that 2 billion year age cutoff. Yeah. So how sensitive is your output and your model to that initial input? So given the understanding that that's the point where, sure, we see oxygen, but prior to that we have a billion, well, depending on who you believe, up to a 1.5 billion years of life that could be producing something detectable that's not oxygen. So how sensitive are your results to that initial input?
Yeah, so they are going to be pretty sensitive to it. Obviously, yeah, the 2 billion year mark, it's fairly arbitrary. It's like an educated arbitrary guess. But yeah, so the biggest, I think, issue is going to be as you, say you go down and you just make it like 500 million years, you're going to have a lot of the stars reaching a maximum like 100% probability. Like most of them are going to then be in that, and so it's going to be a lot less informative. It's much easier for a star to have spent 500 million years in the habitable zone than 2 billion years. And so really, yeah, I guess the thinking here is really just that, by 2 billion years on Earth, there's lots of detectable signals in the atmosphere. And so this is like a conservative estimate saying that if your planet's been in the habitable zone for 2 billion years, it's either got life and it's detectable or it doesn't. So yeah, so that's why we go with that conservative 2 billion years and not something much younger. But it's very easy to change it if a younger age would be preferred.
Our final speaker in this section will be Lily Robenthal, speaking on clearing the air, Titan and Mars as windows into the impact of aerosols on exoplanet atmospheric retrievals.
Mic working? No, not working. Sorry. Thank you. All right, now can you hear me? Cool. Awesome. Thank you so much. Can I grab the clicker, please? Thank you. So hi, I'm Lily Robenthal. I just finished my first semester of graduate school at University of Arizona's Lunar and Planetary Laboratory. And today I'm going to be talking about aerosols in exoplanet atmospheres. So when we're thinking about, come on. Is this not? Oh. Okay, cool. Thank you. All right, pointer is now working. So when we're thinking about exoplanets in the context of astrobiology, like at a conference such as this, we think a lot about atmospheric biosignatures, which are, I'm sure you all are aware, atmospheric species that can be detected in the atmospheres of exoplanets that could indicate the possibility of life on those planets. We are able to study exoplanets through a method known as transmission spectroscopy. Again, I'm sure a few people have already covered this today, and this is really our main method for constraining the compositions of exoplanet atmospheres and potentially detecting biosignatures, just because remote sensing is our option for these bodies. Transmission spectroscopy works in that the planet transits in front of its host star. The starlight shines through the planet's atmosphere, and it gives us a spectrum that tells us the composition of the planet's atmosphere. So every molecule has has distinct spectral features, and that can be relatively easy to pick out if you have only one species that you're looking at spectrally. However, in a system like an atmosphere where there is a mixture of various molecular species, it can be much more difficult to parse, and it can be a challenge to kind of pick out what the components are and actually constrain the composition of an atmosphere. So in order to do that, in order to get actual information about atmospheric composition out of exoplanet spectra, we use a method known as atmospheric retrieval, which involves taking our observations and running a bunch of models based on different parameters, and essentially going through and sort of determining the most statistically likely scenario for our observation through which models match up the best with our observed spectra. And so that is how we can get beautiful spectra like this one from JWST. And there was, I think Cindy showed one earlier that was also really beautiful. You can sort of pick out the important molecular features that are going on, and that, yeah, once we get matched to a model that sort of gives us our best fit. So given that transmission spectroscopy is our method for, really our only method for studying exoplanet atmospheres and potentially detecting biosignatures, we end up in a sort of classic if you give a mouse a cookie situation, where if you give an astronomer a transmission spectrum, they're going to ask for a retrieval pipeline. And when they ask for a retrieval pipeline, they're going to want that retrieval pipeline to accurately and robustly represent the conditions and parameters that are present in an exoplanet atmosphere. So that kind of leads us to the question of what are some of those processes that need to be accurately and robustly represented in these models that could have an impact on our ability to characterize these atmospheres. And this slide is a little bit of a hint. We're talking about clouds and aerosols generally. And we really don't know a lot about clouds. We really don't know clouds at all in the context of atmospheres and exoplanet atmospheres. But we do know that they are ubiquitous in exoplanets as well as solar system bodies, so they're all over the place. Our modeling of them as now is very simplistic. We really don't have a full understanding of how they impact spectra and our ability to derive information from spectra. One of the impacts that we do kind of are able to see already in this cartoon from Barstow is, the clouds kind of raise the lower part of the spectrum and prevent us from seeing deeper into the atmosphere, and that can, block out some of these like important little spectral features that we're seeing over here. So we do know they make it harder for us to see. So really what it comes down to is, so our ability to gain accurate information from retrievals and constrain the compositions of atmospheres and the potential to find biosignatures. That is dependent on how well we can model these parameters. And so how can we improve our models of these aerosols in atmospheres in order to improve our retrieval methods? And one approach is we can look to our neighbors in the solar system. We got a lot of nice planetary friends pretty close by. A lot of them have significant aerosol presence in their atmospheres, like we got Titan, Mars, Venus, Saturn, Pluto, all of these. And of course, solar system bodies have the incredible advantage that we're able to study them in situ, so we can establish ground truth for what's going on in their atmospheres. And this kind of leads into the work that I've just gotten started doing. We are using the vast array of pre-existing occultation observations of solar system bodies to kind of establish a catalog of ground truth for those atmospheres, and then compare that ground truth to our models of these atmospheres to see just how well our models are currently representing what we actually know to be going on in these solar system bodies. So I'm kind of getting started with these two, with Mars and Titan. Eventually, we're going to move on to the others, just to fully have a full comprehensive catalog of the solar system and what the atmospheres of these closer to home bodies are doing, and if it's accurately represented in our models. So there's a lot of data out there. I'm getting started with these. I've really just been starting to dig into the MAVEN data. And I think, yeah, it's really kind of amazing that we have this sort of incredible untapped resource for doing this kind of exploration. Because, yeah, a lot of people have worked on these missions and made this possible. And I think, like, I know the theme of this, this conference is standing on the shoulders of giants. I think it's equally, if not more valuable, to stand on the shoulders of a whole bunch of regular sized guys. Like the people who, all the people who've worked on these missions and who have made this data available and to then further our studies of other things. So yeah, really grateful that this exists as a resource and that I can start digging into it. So yeah, just getting started on some of this. This is some preliminary data exploration from the MAVEN IUVS instrument, which is a Mars mission. We are seeing, in terms of number density of aerosols, kind of a little bit of a mess. It's kind of all over the place. It's not constant, as some models would assume it to be. It's not even super linear. There's just a lot going on. And it's important to recognize this and to see kind of the complexity that is not being represented in models that is present in real data. And yeah, so this is just from the first campaign from MAVEN, so there's a whole bunch more data to dig into there. And yeah, it's really, it's valuable to see, you know, what trends we can find and how our models might be not representing them well and how we can improve. So the second part of this project will then be taking what we've learned from these solar system aerosol profiles and the ground truth and models that we establish, and applying that to our parameterizations of exoplanet aerosols. And again, kind of validating how our models work and if we are indeed getting, you know, as much information as we can out of our spectra. And then, yeah, to wrap up, we currently, our understanding of aerosols in the atmospheres of exoplanets needs to be expanded if we are to derive the most accurate information from those spectra about composition and structure of exoplanet atmospheres. And it's really exciting that we have such a wide array of pre-existing data to kind of start with and use as our ground truth. And yeah, there's a lot of exciting work to be done, and I'm looking forward to getting into it. So yeah, got some references. I want to thank my advisor, Professor Tyler Robinson at University of Arizona, plus the HabLab group, Sierra, Zara, and Arnaud. The France-Arizona Institute for Global Grand Challenges for funding. Appreciate that. I like to get paid. I'm grateful for everybody down at LPL at University of Arizona, and I'm really grateful for the organizers of this conference for putting together such a fantastic event and giving me the opportunity to talk about my, as of now, very fledgling work on this topic. So thank you so much. Also, if any of you out there are familiar with any of the data sets I mentioned, I would love to talk to you because I'm trying to find ways to reduce a lot of that data. So if you know about it, talk to me. Yeah, thank you. I'd love to take any questions.
Hey, Kara Pasciata, Hopkins. I'm wondering if you've thought about using any of the data from the cosmic dust analyzer on board Cassini?
Yeah, I think we are going to use some of that, yeah, when we get into the Cassini data for Titan and Saturn. Yeah, cool. I think that's, yeah, one of the things.
Stephen Coffey from Columbia University, and I'm wondering if there's like clear-cut definitions of the differences between like clouds and hazes. Yes. Is it like the opacity of like clouds that are completely opaque and hazes are not, or?
It's kind of a situation of how they're formed. So clouds are formed through condensation. That's how they're identified. Hazes are formed through photochemical processes, and then dusts are like aeolian, like wind-driven aerosols. So that's kind of how they're divided. It's by sort of their mechanism through which they're formed. Yeah, it's a good question.
Last call.
Thanks for that talk, Fletch from the University of New South Wales. If you skip to your preliminary results graph really quickly, I'm just wondering, you see there's two lines that appear kind of linear in that data. Are those like bounds of detection of that instrument, or what is causing that?
That is a really fantastic question, and at this point I do not know. I'm only just starting to get familiar with this data set, so that's something I would be very interested to figure out as I go forward. Yeah.
Excellent.
Yeah.
Thank you.
All right, that was our last talk for the session. We have Panera waiting for you outside, salads and sandwiches. We're back at 1:30 for Ice Ice Baby. Is it charged? No problem.
Thank you. Was it yours, right?
Yep, thank you.
All right, we're going to get started for our next session. This next talk session is Icy Worlds, or Ice Ice Baby. The first talk today, I'm sorry, I'm just laughing. The first one will be from Jennifer Yak, and she'll be talking to us about enhancing the search for life on icy ocean worlds through high pressure experimentation. Take it away, Jennifer.
Well, thank you. Oh, wait, can you hear me? Is this on? Okay, perfect. Thank you so much. My name is Jennifer. I'm a second-year PhD student at the University of Illinois in Chicago. Hold on, I'll fix this. Okay, so I'm going to be talking today about high-pressure experimentation, specifically evolving a strain of bacteria to cope and live under extremely high pressures. Okay, so understanding how life evolves and survives under extreme conditions is really important for astrobiological study, as we all should know. These extreme conditions include things like high temperature, low temperature, high salt concentration, high pressure. When we go to other worlds or other off-world environments, the environment is way different than what we're going to find here. So I'm, again, talking about high pressure. Earth supports life, as far as we know, up to 125 megapascals of pressure. This is like the bottom of the ocean. So the life we find at the bottom of the ocean is generally 110, 125 megapascals that it's living at. But high pressure environments are going to be relevant to the icy moons that we're currently researching, such as Europa. It's thought that Europa's subsurface ocean is 110 to 260 megapascals. So this is going to be way higher than life as we know it can tolerate. And then Titan is up to 800 megapascals at the bottom of its subsurface ocean. So again, way higher than life as we know it. And then Enceladus as well, 1.5 to 10 megapascals, so a little bit lower, but still high pressure. So I want to talk a little bit about some previous experiments that we have done. We used the bacteria Shigella oneidensis, and we put it under 150 megapascals of pressure. We did two different experiments. We did one at 15 minutes, and we did one at 2 hours. Both of those experiments yielded survivors, and then we did transcriptomics on the 15-minute experiment. So our results from the transcriptomics are showing upregulation of DNA repair genes, which is to be expected. So organisms that are known extremophiles, or organisms that can live in really extreme conditions, they utilize DNA repair mechanisms to cope with those extreme conditions and survive. So this was expected. We also saw changes in fatty acid biosynthesis regulation. So we saw a little upregulation of branch chain fatty acid biosynthesis. Again, this is to be expected. The branch chain fatty acids would be incorporated into the membrane to give the cell membrane fluidity under high pressure. And then we also saw a downregulation of the ribosome, recycling factor. This just means that the cells, after 15 minutes of pressure, were starting to turn off protein production. So it looked like their focus was more on protecting the DNA and protecting their membrane than actually building proteins. We did longer-term experiments with Shigella oneidensis for 2 weeks at 150 megapascals, and we had no survivors from that experiment. So my research is hoping to expand on this by not just throwing this bacteria under extremely high pressure, like straight off the bat. I'm trying to make it evolve to cope with these really high pressures. So I'm doing this with a technique called adaptive laboratory evolution. And this is pretty straightforward. You take an environmental condition that you want to evolve your organism to. So in my case, it's going to be high pressure, but you could do this with anything like temperature, high temperature, low temperature, salt, any extreme condition. So you take your organism, you put it in that condition, and then you slowly increase or decrease it. So in my case, I'm doing high pressure, so I put it in at a low pressure, and I slowly am increasing the pressure. This is going to hopefully promote the cells to become more fit to this condition. So hopefully we'll get a mutation that allows the organisms to survive that condition. and that will be reproduced throughout the population, and then we will have an evolved strain of bacteria that can handle this high pressure. So bacteria reproduce really quickly. This is why we're using bacteria to do this. The organism I'm using, Shigella oneidensis, it has a doubling time of 40 hours. So that means in 40 hours, that population will double in size. So hopefully, we will get some mutations fairly quickly that will allow it to cope with this pressure. ALE, or the Adaptive Laboratory Evolution experiments, also gives us insight into how these organisms evolve or adapt to these conditions. Oops. Okay, so to do this, we use a custom-built high-pressure panel made by Harwood Engineering. It's an air-driven hydraulic pressure system. This is what controls the pressure. It gets pressurized through this panel here, and then the pressure gets put into the vessels. These are the vessels that the experiment actually goes into. This system is unique from other high-pressure systems because it can go to extremely high pressures. We can reach 2 gigapascals, and our vessel it can hold more culture than most other high-pressure systems. So our system can hold about 15 milliliters of culture, where other systems can hold maybe a mil tops. And then we also make, in our lab, these fluorinated ethylene propylene bags. This is like a Teflon bag, so it can withstand the pressure while it's in the vessel. And this is what we put our bacteria culture in. Okay, so the goal of my experiment here is to evolve a strain of bacteria to withstand 150 megapascals or higher of pressure. And not just withstand it, I don't want it to just simply survive. I want it to be able to grow and reproduce under this pressure. So how I'm setting this experiment up, I'm using, again, Shigella oneidensis MR1. So this is the same bacteria that we used in our previous experiments. I started 2 different experiments, basically. I started one at exponential phase, and then one at stationary growth phase. And then for those of you here who are not biologists, we can think of exponential phase as this organism has all the resources it needs to reproduce very quickly. So its main focus basically is to reproduce and make as much bacteria as possible. And then the stationary growth phase, this is when those resources start to run out and the bacteria switches from trying to reproduce as quickly as possible to just simply surviving. So it turns on a whole different suite of genes. We call these the stress response genes. And I wanted to do this just to see how these 2 different growth phases affect the initial pressure tolerance. All of our previous experiments were done at stationary phase. So I wanted to see how they handled it at exponential phase. So I grew cultures in a broth media. I put them in those little Teflon bags. And then I started the experiment at 15 megapascals of pressure. And then here's just a little schematic of how the experiment works. So it stays in the high pressure chamber for 2 weeks at the pressure. I take it out, and then I sample that culture. I do some protein quantitation. I do some cell counting. I do different microscopy, viability assays, different staining techniques, which I'll talk about later. I also start a backup culture just to make sure that this bacteria actually survive that pressure. And in case anything were to go wrong in the pressure chamber, if a bag were to break, I have something I can go back on. From that culture that came out of the pressure, I take 1 milliliter of that culture and I start a new bag with it and mix it with 3 milliliters of fresh media. So I basically take it out of the pressure, give it some more food so it can continue to grow, and then put it back in the chamber. And then we put it back in the pressure chamber at a slightly higher pressure. Okay, so I said I wanted to make sure that this bacteria was actually growing under pressure. This is one of the goals. I don't want it to just simply sit there in a dormant state, surviving the pressure and waiting till it comes out to grow. So one of the things I do is a protein assay. So this graph here is just showing the protein growth during these 2-week periods under the pressure. So on our x-axis, we have the pressure of each experiment in megapascals. And on the y-axis, I have the protein concentration of growth. So this is how much protein it gained while it was under pressure for 2 weeks. The blue bars are going to represent the exponential phase experiment, and the purple bars are going to represent our stationary phase experiment. So we can see in the beginning, the stationary phase was doing much better at coping with the pressure and growing under pressure. But as the experiment continues to go on, it evens out with the exponential phase. Okay, and then, oh, this looks different. Okay, sorry, this looks different on my computer. Sorry, guys, I'll still walk you through it. Okay, so this is another graph showing the protein growth under pressure. So on the left side, we have the exponential phase. On the right side, we have the stationary phase. That is supposed to be 2 separate graphs. The x-axis has our megapascals, or pressure in megapascals, and then the y-axis has our protein concentration after the experiment in micrograms per milliliter. So we have the circles here are going to be our control group. These are the ones that are not pressurized. And then the triangles, we have our experimental group, what I also call the survivors because they have survived the pressure. And as we can see, the control group is doing much better at growing outside of pressure than the pressurized ones. But I just want to make a note that the pressurized ones are still growing. And they're probably growing a little bit slower because they're under extreme pressure. Okay, sorry, this is all messed up. Okay, so we want to measure protein, or we want to measure growth of the bacteria that are under pressure. Again, this is one of the goals. We do this in several different ways. So we do protein quantitation. For this, I use the BCA protein assay method. It's a colorimetric protein assay that uses a spectrophotometer to determine the protein concentration in a sample. I also do microscopic measurements. So I take the sample, or a sample of the culture before it goes under pressure, and I look at it under the microscope and take measurements of how big the cells are. And then I take a sample of the culture after it comes out of pressure. And again, I take measurements of how big the cells are and what they look like. So what we're seeing on the top picture is before it goes under pressure, and the bottom picture is after it comes out of pressure. So we're seeing that these cells get longer, more filamentness, a more chain-like pattern. And it's thought that the pressure, so the cells, when they're in pressure, they're doing everything to grow. They're building biomass. We see that they're building biomass with the proteins. They're doing everything to get ready to divide, but it's thought that those stress response genes are turning off the gene that makes the septum that physically divides the cell. So it's thought that because they're stressed out and under pressure, they can do everything to divide except physically divide. Okay, and then we also do cell counting, and we use the fluorescent stain DAPI to do this. DAPI readily enters the cell and it binds with the DNA, and it will make the cells fluoresce under the microscope. So we can count how many cells there are. So if we have more cells in our culture that comes out of high pressure than we did that went in, then they obviously are reproducing under pressure. We also not only want to measure growth, we want to make sure our cells are metabolically active under pressure and that they're alive or viable. And to do this, I start that backup culture in the tryptic soy broth media, and if they survive the pressure and they're growing, that media will turn turbid. So the bag on the right here, that is going to be turbid. Those are cells that you're actually seeing, the bacteria. And then the bag on the left is, it's not turbid, nothing grew in that one. Okay, we also use another stain, it's called calcine AM. This stain will tag bacteria that are metabolically active. This dye works by readily going into the cell through the membrane, and if the cell is active, it's producing an enzyme called esterase. So esterase will bind with that calcine AM dye molecule, it will cleave off a piece of that, and then that dye will start to fluoresce under the microscope. So the cells that we can see in here are metabolically active. And then another one that we are working with is the live or die viability stain. This one works by entering the cell through a compromised membrane. So if there's like a hole in the membrane or a pore in the membrane, that dye will go in, it will bind with the DNA, and it will flag that cell fluorescently. Our problem with this is it's thought that under pressure, the cells develop pores in the membrane or little holes in the membrane that are not necessarily deadly, that cell might be able to repair and still keep on surviving. So we are currently trying to see if this is actually going to work with our experiments or not. Okay, so our next steps for this, I'm currently working on doing some genomics to track any changes to the genome. We have a genome of this bacteria annotated already that has not been pressurized. So I'll be able to compare my genome from my bacteria that's currently under pressure and see if there's any changes in it, if there's any type of evolution happening. Also, Shewinella, in the Shewinella family, there's another species called Shewinella benthica. It lives at the bottom of the ocean. So this is one of those organisms that can tolerate 110 MPAs or 125 MPAs already. So I would also like to, if there are genetic changes to my organism, my strain, I would like to compare that to the genome of Shewinella benthica and see if those changes are the same or if they've come up with different ways to adapt to that high pressure. We are also working on transcriptomics to compare this strain that's currently under pressure with the 15-minute 150 MPA experiment to see if it's turning on the same types of genes, if it's using the same mechanisms to cope with that to cope with that pressure or not. And then I also want to do flow cytometry to check the accuracy of our cell countings and our different staining techniques and see if these are actually working and good techniques to use. Okay, and then some takeaways from this. So by using this ALE method, we've been able to grow the strain of bacteria at increasingly higher pressures. It's currently in the high pressure chamber right now as we speak at 42 MPAs. It's still surviving, it's still alive, so it's working so far. I know we're not anywhere near 150 MPAs yet, but we're slowly getting there. We saw earlier that the experimental strain is growing slower than the control group, but this is to be expected. Again, it's thought that the pressure is making decreasing the growth rate. And then by using a combination of staining methods and the protein assay, we are able to show that this protein is not only growing or not only surviving, it's growing, building biomass, and reproducing under pressure. And with that, I just want to thank all of you, the audience. I want to thank the organizers for AbGradCon 2024. I'd like to thank everybody in my lab, the EDGE lab at the University of Illinois in Chicago, Dr. Fabian Koenig, one of our undergrads, Ty. He spent countless hours with me trying to do this and working with the pressure machine. And then a special thanks to Dr. Michael Malaska at JPL. And then if anybody is interested, I've heard a lot of talks earlier about microbes and bacteria, and if anybody's interested in working with high pressure, feel free to reach out to me. My email address is up here along with my website.
All right, we have about 2 minutes for questions if you guys want to come down here.
Hi, Abby Deering, Georgia Tech. It's a really interesting project. I was just wondering, I think you might have mentioned it, but could you talk a little bit more about how you're sure that your cultures are staying in the exponential or stationary phase when they're there for 2 weeks?
That's a good question. I did not talk about that. They are not staying in exponential. Because we're feeding them, they're going right back into exponential as soon as we restart that. It was more of, I wanted to see at the very beginning how exponential and stationary compared to handling that initial pressure. But yeah, ever since that very first 2 weeks, they're all in exponential now.
Thanks.
All right, we got time for one more question.
Very interesting talk, Sarah from Michigan State. Have you seen biofilm formation within your cultures after applying pressure?
Not after applying pressure. In the control groups, though, they do form biofilm. but I haven't seen it under pressure. And that might just be because they're growing a lot slower than the experimental groups. And maybe if they were left in longer, they might form a biofilm, but Chivinella does form biofilm.
So, and you're running all your experiments under aerobic conditions, right?
Yeah, anaerobic.
Anaerobic.
Anaerobic, sorry.
Thank you.
Give another round of applause for Jennifer. Okay, our next talk will be from Claire Elbin, talking about anaerobic biological formation of manganese oxides in the Gulf of Mexico deep hypersaline anoxic basins. Take it away, Claire.
All right. Thank you, Taylor. All right, I'm Claire. I'm a fourth-year PhD at Georgia Tech, and I'm going to talk about a really big collaboration with the Oceans Across Space and Time team, where we went to the Gulf of Mexico DHAB called Orca Basin. Okay, so microbial manganese oxidation occurs in soils and sediments as well as freshwater and marine systems. So it's pretty much everywhere. And some good examples of aquatic manganese oxidation by microbes. Please? There we go. So in the basalts at the Lohe Seamount, there's a very diverse group of microbial communities that are catalyzing this. And they sort of sit on top of these manganese oxide nodules that they produce and form a biofilm around it. So these are SEM images. And remember what these look like. It'll come back later. At Caltech, their tap water, they were able to isolate a bacterial chemolithoautotroph that uses manganese oxidation. And so what's really cool about manganese oxides is we're going from the insoluble form of manganese 2+, to the insoluble particulate form of manganese 4+, and it turns this really nice purple color. So it's very, very conspicuous. These are the manganese nodules that these guys produce. At our lab at Georgia Tech, we have a very thriving, happy leptothrix community in an old filter system that we don't use anymore, forming lots of manganese oxides. And perhaps the most interesting to me is the Black Sea has a suboxic basin where a lot of really fast manganese oxidation is occurring via these microbes who are thought to use even just nanomoles of oxygen to drive this reaction. So overall, there are quite a few different ways to form these particulate insoluble manganese oxides. And overall, it's thought that this really needs oxygen to work because it's very thermodynamically difficult to form. So because of that, the formation of manganese oxides is thought as a really good biosignature for microbes forming it, and it's also used in the sedimentary record for oxygenation on Earth. But there are a few ways to form manganese oxides anaerobically. And in particular, it is thermodynamically feasible to do this as a microbe with denitrification. It just hasn't really been shown yet, but it's thought to occur in anoxic marine systems that can support this type of metabolism. Why you all might want to care. So I'm really more a microbiologist, and I'm going to always say it's good to know what kind of metabolisms can happen on Earth so we can have legitimate, real hypotheses if we're looking at stuff elsewhere. So in the example of Mars, there is biologically useful nitrogen in the form of nitrate that's been found in Gale Crater, as well as manganese oxides that can't be explained alone by any sort of other just regular chemistry going on. So deep hypersaline anoxic basins, probably a good place to look for this kind of metabolism because they are 8 times as saline as typical marine seawater.
This is because evaporitic deposits open up and they form these giant hypersaline anoxic waters, super, super salty. Don't go into a brine pool, you'll end up like this guy. Wouldn't recommend it. But there's also a halocline that is right above this brine water, and there are some, only in the difference of a meter, very, very strong geochemical changes. So we went to the Orca Basin off the Gulf of Mexico. This is the anomaly of salt, so this is the evaporitic deposit, and it fills this entire basin with that super salty brine water. We took an ROV and we did, typical CTD casts as well. Veronica was on the ROV team, and they were really cool because they went down into the brine pool, and that's never been done before. So, Veronica, you're my hero. What I really like about Orca Basin as well is that there is this insane peak in particulate manganese oxides. So if you're thinking like a microbiologist, I can't just look in the water and find the microbes. I like to call these metabolic crumbs. I can't see the microbes, but I can pretty much guarantee you something biological is making this happen. Then you go out to sea. So when we're chasing metabolic crumbs, for the rest of this talk, I'm going to be focusing on this 2,200 meter depth, and I'm going to explain to you why. So this is right at the brine seawater interface. So this is right before everything gets really, really weird. So pH starts to have a little hump and then decreases here. Temperature is right at this part of starting to increase. So this is at 8 times saline. Dissolved oxygen is completely gone at 2,200 meters, and we're just starting to see that salt go crazy. Really interesting to me is this right here is indicating we're in the zone of denitrification. So that means oxygen's not being used, nitrate is being used in its place, and soluble manganese 2 is available to be used. So if we overlay this older cruise that went out there, 2,200 meters is also that point where this particulate manganese oxide peak occurs. So very interesting spot for me to want to look at. So you go out to sea, and then you sample stuff with all your friends on the CTD. The first thing that I did, I wanted to identify manganese oxides and see if cells were hanging out around them. So this is a depth profile. This is the deep brine. Really, really yucky. Smelled weird too. But this is at manganese oxide peak. So you can kind of see there's already this dark purple occurring just from 45 milliliters taken. So I used a method used by a previous grad student in our lab that was developed called simultaneous staining with LBB blue. This will only stain manganese 4 in the form of a manganese oxide. What makes it this nice, pretty blue. You can point out the exact spots that these oxides are. And you can use Cyber to stain the cells. They'll turn this nice green. And then you can overlay it and see if there's some co-location happening. So for 2,200 meters for us, we saw a lot of cell conglomerates looking like this. You can already sort of see some minerals inside these conglomerates. This is that same exact same spot here. It's turning blue with that manganese. This is looking like where it is, but this might also be manganese here. And then when you overlay it, you can see that the manganese oxides in the cells are very, very closely located, if not touching. And what we found overall was that manganese oxides are both present and primarily co-located with cells at 2,200 meters. And this was done with 2 really great undergrads at Tech. And basically, if you saw manganese oxide, you were pretty much guaranteed to see a big clump of cells hanging around it or next to it. So the next thing I wanted to do was I wanted to enrich cultures for manganese oxidation and nitrate reduction. I wanted to see if I could get these bugs back in the lab to do this thing that I think they're doing. So I took a lot of bottle cultures at sea with an anoxic overflow method, basically just made sure there were no bubbles. In the cold van at sea, where I spent all of my time, I added dinitrogen gas to sparge out the headspace and then added anoxic nitrate. So this first set of samples, and for everything else I'm talking about, I was living in the glove box doing. This first set of samples, this first transfer, was producing these kind of larger clumps of manganese oxides, which was a little bit different from what I was seeing in situ, but it was still doing something. So then I did a bunch more transfers in a 2-to-1 ratio of nitrate to manganese 2 and kind of measured the fluxes and changes, see if I could see if they were doing what I was hoping they were doing. So it looks like they are. These enrichments from 2,200 meters are oxidizing manganese 2 to manganese 4, or as a manganese oxide, kind of regardless of how much manganese 2 I was giving them. They were definitely increasing that amount. I want to point out this is in nanomolar. I don't know how well you can see this, but it kind of looks like a gross snow globe at this 30-day period where you're seeing these little particles appear. I was also seeing that there was concurrent nitrate reduction going on. So there was a lot more nitrate being reduced, but this is probably not a pure culture yet, so I think pretty much everyone was very happy to have a lot of nitrate all of a sudden. So we've shown this, and now we wanted to look more at the mineral itself. In particular, we used SEM XRD, which was to get nicer photos of the microbes, and then to see where exactly the minerals were, and to sort of detect features. We also did synchrotron X-ray diffraction, and that is to look a lot more at the mineral composition itself. Oh, and I did this in collaboration with Ray Kai at Georgia Tech and Dr. Tang's lab. So think back to those SEM images. This kind of looks like a nodule, I think, and there are cells all around it forming some sort of biofilm. I was really excited when I took this and I sent it to my parents, and they said, "Why are you taking photos of a nose?" But the nose does have manganese peaks, so this is a manganese mineral. So another type of morphology we saw a lot was this sort of stacked mineral structure with cells just kind of like stuck around. This is also a manganese mineral structure. So we were seeing two different types of structures, but they were both manganese and they had cells. So then looking at the mineral itself with that synchrotron XRD, this is very new, and I have not read enough about this to answer hard questions. But we saw a strong manganese and iron oxide peak with this data. Zooming in on the manganese oxide peak, we're working on sort of figuring out with some controls how we can better look and see what exact type of mineral this is. I think it looks a little bit like this, but much more to come on that. But overall, maybe manganese MnO2. So overall, manganese oxides are highly associated with cells from that 2,200 meter peak. I'm providing evidence for potentially a novel metabolism of anaerobic biological formation of manganese oxides that occur with nitrate drawdown, and the produced oxides have cells covering them. I'd say this is a pretty good potential biosignature for anaerobic microbial manganese oxidation. This is, like I said, very highly insoluble, and so we're really looking more into the mineralogy and seeing if it's just very unique and different from other manganese oxides that have been recorded. And again, finding hypersaline metabolisms with these kind of funky metals and stuff is really great hypotheses for metabolisms or understanding life maybe elsewhere. So what I have in progress, I've sent off some 16S sequencing of the transfers just to see who's there. There was a secret experiment I didn't tell you about that we did shipboard, where we incubated some stuff with and without manganese and nitrate, gave it some HPG to try to do BondCat, and JGI, this is really all thanks to Emily Skoog, who got this money, but JGI is doing microdissection of the particles so they can just sequence the cells on the particles. Miguel de Marais, who's at Scripps as well, is going to be looking at that simulstaining process, but then using BondCat tagged cells with that LBB stain. And then we're going to try to do TM-EDX of the minerals. So a lot of people to thank. I'm just going to really quickly thank the RV Point Sur crew and the research group there. It was a really great time, and thank you for your time, and I'll take any questions.
Okay, we've got about six minutes for questions. Anybody have any questions? Maybe. Do you have a question? Okay, I'll come over there.
Thank you so much. Great talk. Could you talk a little bit more about how, the various ways in which you imagine it applying to these off-world systems like Mars, like you mentioned?
So for Mars, that's going to take too long. So for Mars, in the Gale crater, there's nitrates that have been seen. More on the manganese oxide cycle. So this is rocks that have very high enrichments of manganese oxides, and there's been a lot of look into it being a halogen cycle that's kind of driving formation of manganese oxides. That was originally used as an argument for Mars being oxygenated, because on Earth, manganese oxides are basically synonymous with an oxidized Earth. But sort of the idea now is that it was an anoxic system and there was very active halogen cycling driving that, but that still thermodynamically doesn't quite match up, as I understand. So I think finding a hypersaline, biologically driven oxidation of manganese kind of adds more to that sort of discourse of, well, someone can, under hypersaline systems, sort of point the way to that. Does that answer it?
Cool, that was awesome. Thank you so much.
Yeah.
Hey, Claire, that's great work. It's really awesome. I was wondering if, I don't know if you can tell from the SEM images, but do they encrust, or is it do the cells get encrusted with the manganese oxides, or not at all?
That's what we're trying to figure out with TEM, because the simultaneous staining, it looks like the cells kind of have just like splotches of manganese inside what looks like a biofilm. This looks like a biofilm of cells kind of around a mineral, which could also point to manganese oxidation is also a very happy microbial process. So these might just be manganese reducers here. And then, yeah, this one I'm not really sure. I haven't seen, I know manganese oxides also work well as kind of like a protectant for cells, so some will encrust manganese oxides around themselves, but I never saw anything that was a cell with manganese. It was always more manganese with cells engulfing around it.
Okay, and then secondly, do you have any sort of hints as to any particular enzymes you might suspect? Is this like an open space, or are they reusing something else maybe?
There is, so Brad Tebow has done so much work on this. There's a multi-copper oxidase that's sort of being pointed to as what could be driving this kind of metabolism. I know there's a couple other oxidases that have been pointed to, but nothing that's like a very clear thought out pathway.
We'll wait for the transcriptomes.
Exactly.
Hi, Ben Vegas here at Cornell. Can you go back to your slide where you have the potential nitrate reaction that you think might be going on here?
Oh, dear God.
Sorry,
No, you're fine.
All the way back to the beginning here.
The jokes aren't funny in reverse.
Okay, so the thought is that this is some kind of form of denitrification where you're releasing N2?
Yes.
Okay. So then my question is are you ever gonna be doing this again, and can you measure the isotopes of that N2?
That would be very cool. Right now, I am setting up to measure, so we have a GC-ECD, so I can measure nitrous oxide, and most denitrification is a little bit leaky. So if I'm seeing nitrous oxide forming, I can sort of extrapolate through kind of doing mass balance that, oh, okay, there's some denitrification going on, but nothing with isotopes, no.
My thought process is by monitoring the N2 species, that can help you trace back to this process rather than, say, nitrate being taken up by something else
Right,
in your body.
right.
And as a deep time nitrogen person, I just want to know what the isotope effect is.
Yeah, it would be cool to know. Yeah.
Thank you.
Give another round of applause for Claire. Okay, the last talk session will be by Hypatia Meraviglia, and she will be talking to us about what could amino acids on Enceladus or Titan tell us about detecting life. Take it away.
Cool, thank you. Can you all hear me okay? Y'all all right? Okay. I'm Hypatia Meraviglia. Oh, I'll grab the clicker. Cool, I'm gonna talk to you about amino acids. I'm a second year PhD student at ASU. So the work that I'm about to tell you about is like very much still in progress. It's still cooking. And so I am so excited to like get y'all's feedback. And if there's something that I like missed or haven't thought of, I really want to hear about it. So I'm very excited. So I think probably like most of us in this room, the work that I do is very profoundly influenced by the sci-fi that I watched growing up. And especially about this project, I think a lot about this one episode of the original series where the Enterprise runs into this life form that is silicon-based, and they don't realize that it's life at first. And they don't realize that it's life until Spock is able to directly communicate with it. And I think that this episode like is in conversation with like the central question of astrobiology, which is how do we find things that we don't know what they look like? I think it's our responsibility as astrobiologists to cast our net as wide as possible. And so I like to think about other things that life could use, like other kinds of life that could occur. And so we'll talk about amino acids. So my background is in like atmospheric chemistry. And so when I think about that question of looking for life that we don't know, I think about what chemistry could be biochemistry. And of course, that has profound implications for a lot of aspects of astrobiology. It has, biosignatures, right? What is a fingerprint of life? What is the definition of life anyway? I think that if you asked 5 astrobiologists what life was, you would get 6 answers. And it also gives us profound context for Earth, whether there is sort of one way to get by as a biological system, or if there are many possible ways to get by. Cool. So for Earth life, there are about 20 amino acids that are coded. That means they're included in our genetic code. They hold information for us. They allow us to reproduce. But there are lots of amino acids that are not coded. And we don't really know why they're not coded. We don't really know why we ended up with the 20 that we did. We don't know why we ended up with 20. And so I like to think about what other amino acids could be involved in life, and how do we measure that, and how do we compare sets of amino acids to each other to figure out which ones could be biological and which ones cannot be biological. So my background, like I said, is in atmospheric chemistry, and so I've been thinking about Titan and Enceladus for a few years, so that's where I decided to start. We also have a lot of really cool studies that have been done about amino acids at these sites. So Titan, for example, we have pretty consistently been able to reproduce the production of like simple amino acids from atmospheric simulations in chambers, but we haven't like directly detected it on the moon. So there's like a lot of thought about that. That's really cool. But so we have like these sets of amino acids that we think could occur, but we haven't seen them. Really similar for Enceladus. Yeah, like we have the ingredients there. We think that it might be able to happen, but we haven't directly detected it. There was this really cool study in 2017 by Guzman and colleagues
who proposed that maybe cometary material could have deposited amino acids onto the moon and introduced them to the system. So they had like this list of amino acids they thought could be there and concentrations for it and recommendations for future missions, which is really exciting. So even if we sent a mission out there, if we sent a worm to Enceladus or we send Dragonfly to Titan and we see amino acids, what is that going to mean? Like what does that tell us about astrobiology? What does that tell us about the astrobiological potential of these sites? How do we contextualize that information? So I think one way that we can do that is with assembly theory. And assembly theory is a way of thinking about how we construct an object from its constituent parts. So here's a couple of amino acid examples. We have glycine and arginine. So this is all of the steps that you would have to go through to build arginine. They're not chemistry steps. They're like Legos. Like you have a bucket of Legos and you're sticking them together, and then at the end, you build arginine. So this whole number of steps is called the assembly pathway. And the number of steps you have to take on the shortest pathway, the most efficient pathway, is called the assembly index. And that's one way that we can measure how complicated something is. So for example, we can just trivially do this with the 20 amino acids that we have here coded. So we have molecular weight on the x-axis, and we have path length, which here is assembly index basically, on the y-axis. And so we can see that we have this nice consistent trend as things get bigger, it takes more steps to build them. You would expect that. And so we can also see that it does not take very many steps to build these things because they're really simple. It's glycine is 2 steps. And tryptophan, the most complicated one, is 14. So they're small and they're easy to build. So, but what I'm interested in is not just the pathway as a whole or the number of steps that it takes, like some other studies have been interested in. What I'm interested in is the fragments themselves, the pieces, the Legos that we're adding together to get to this final product. I'm interested in them because it's something that we can directly measure with a mass spec. So, lots of precedents for putting mass specs onto missions. And by breaking something apart, by fragmenting it, we can count the number of fragments, and we can directly measure this. So it has direct mission relevance. So how do we apply this to amino acids? So here's the pipeline that I've been developing and working on, and we'll talk to it. It's big and complicated, but we'll go step by step. So first, I start with some amino acids that are involved in a reaction or that have been proposed for some kind of system. So that might be the amino acids that Guzman suggested. That might be the amino acids that we've been able to form in Titan atmospheric simulation chambers, that kind of thing. And then I break them into pieces, as much as I possibly can. And then I build possible molecules from those fragments. So I have my bucket of Legos, and I stick them together randomly, and I get other things that you could have gotten from those same fragments. In a system that has those fragments, what other things could have been built other than these amino acids? But these fragments, you might have noticed on the pathway, these are not things that would be stable. If you put them out in the world, they would fly apart, some of them. They're not thermodynamically stable. So when I do this part, what I get out, not all of these pieces are thermodynamically stable. Not all of them could occur in a real system. So I want to ask chemistry what chemistry thinks as well. So first, I go through my Legos, and I sort out the ones that are not thermodynamically stable. I calculate their affinity. And then I calculate the abundances for each fragment based on the reaction conditions that we did. And then I speciate the fragments. So I stick them together according to chemistry rules, and I get out a different set of things that could possibly be built from these fragments. And of course, for that, I need my experimental conditions, like pressure, temperature, and pH. Here's where we get the geochemical system that's affecting what could happen there. So now I have a couple of different lists for other things that could have been built from these items, but were not. So I'm able to map them across the space of what parts do they share, what parts do they not share. I'm able to rank them by the assembly index that I was talking, how complicated are they? And also their thermodynamic affinity in different environments, how likely are they to occur according to thermodynamics? And it answers some central questions that get at what I'm curious about. What other objects could be built from the fragments but weren't, and why didn't we see them? And what's the relationship between this abstract assembly space of things that may or may not occur and chemistry, where we have these thermodynamic rules that's controlling what can happen? So coming back to our big question, this can give us some context for Earth. So I showed you those assembly pathways that are all these little steps that can get there.
if we have, that's for one object. If we have a set of objects, we can think about the joint assembly space. So it's all the steps that you would have to go through to build that set of things. Some of those steps will be shared, right? Some of these amino acids have pieces in common. And so if two objects have a lot of things in common, their joint assembly space will be more efficient than if they're very different. So here's two sort of abstract spaces to explain what I mean. So we have path A, where we're making objects, and path B, where we're making objects. So let's say we go to the system and we observe some things. We can compare these two different pathways by their end objects, the copy number, how much did we actually see there, what's the abundance. We can compare them by the assembly index, how complicated are they. But what I'm really interested in is comparing them by the reuse of parts. How related are these systems within themselves? How related are the amino acids, right? Is it true that life consistently prefers a set of amino acids that are really similar to each other? So you can build them quite efficiently together without a lot of energy expenditure? Or is it true that life prefers amino acids that are pretty different from each other that might be able to fill many different functions? We don't know, and so I'm really curious about that as I work through my pipeline. So here's an example of what I mean. We've got our nucleobases here. So you can see there's some pieces in common that it suggests that they are pretty similar to each other and can be built together pretty efficiently. So that might be one way that we can tell an abiotic system from a biotic system by how many parts are shared, how efficiently they can be built together. So my next steps, I am currently working through the pipeline, developing all the little code pieces using some glycine-glycine reactions that we did just in the lab. But once it's all complete, I want to run through the coded set of 20 amino acids so that I can compare that to the proposed or observed in analog sets for Titan and Enceladus, those Guzman sets and Horst sets that I was talking about earlier. I'm curious about the reuse of fragments within the sets, what thresholds can be set for the assembly index and the copy number of detections, and also whether amino acids could be built from high-use systems but weren't. Why didn't we see them? Yeah, cool. So I want to end on this because this gets at the heart of the study and why I think it's important. So like I said, I think it's the responsibility of astrobiologists to cast our net as wide as possible, because the risk of missing life because we didn't know it was life because it's so far from us is simply too high. The symbol that's overlaid on this is from Vulcan philosophy, which is weirdly well developed. And it stands for infinite diversity in infinite combinations, which is the central dogma of biology, in my opinion. That we live in a world of combinations and recombinations, and the pantheon of molecules and ideas and people should be celebrated and protected and kept safe. I want to say thanks to all the people that I work with. They are so wonderful. I came from a very different background, and so they've really helped me get oriented in this new space. And also, I want to say that my work would not be possible without the union that I'm in. I would not be able to do the work that I do without the raises that they fought for, and you should join your local union.
All right, we've got about 5 minutes for questions. Question, okay.
Are you considering using machine learning algorithms or neural network potentials for predicting different connectivities of the amino acids?
That would be really cool. That's not something that I've done yet, but I think it would be really interesting, especially because we have these massive data sets that we're working with, JGI or KEGG or something, really tremendous stuff that would be interesting to train an AI on. But I myself have not done that yet, but that would be so cool.
Hi, Ashley Hartwig from Florida International University. What are you using, or what do you plan to use to calculate the thermodynamic stabilities of your reactions and your fragments? Because I think it's a good idea, and I really like the path that you're taking, because it's kind of like going in reverse, but breaking it apart, like you said, with Legos. So I'm just curious, how you're going to calculate those stabilities.
Yeah, absolutely. This is what I was working on last week. It's been a steep learning curve for me, but I use ASE and Orca, which are two tools that you can use to optimize the geometries of molecules. So they do a lot of quantum thermodynamic calculations with DFT and stuff like that, to wiggle the parts of the molecule to get it to an optimal geometry, and recalculating it at each step to try to figure out where thermodynamically stable is for that molecule. So I use ASE and Orca. But then once I have those stable fragments, I use a tool that was developed by a professor at ASU, Everett Schock, called WORM. And it is, I see some of y'all are familiar, it's really great. It's able to do calculations about things that are on like Earth systems, like submerged in water, that kind of thing, to, like I was talking about, speciation, stick them together and figure out what reactions would happen.
Hi, I'm Rory from CU Boulder, and I really like this talk, thanks. My question is if you have any idea that with this assembly and thermo approach, if you could address this question of chirality and preference for chirality in biology.
That's so cool. I don't know. I don't think so. Well, I don't know. I think that probably the difference in chirality might make a difference in the thermodynamics and like the way that they combine, but I'm not sure. That's not something I've thought about, but that would be so cool because that's such a huge open question, similar to like, we don't know why these 20, we don't know why they're all sort of left-handed, Yeah, that's so cool.
Any more questions? Any online? You have another one?
Hi, I'm Shekhar from George Washington University, and your study was so good, and you're planning to like work on amino acids. So I'm just curious to know about like these amino acids have different natures, like non-polar, polar, and they have different side chains. Like, so how are you gonna deal with that problems on like you're working for amino acids for Titan? So I want to know that.
Sorry. What?
No, I want to know that how are you going to work with those amino acids? Like you said, the next steps will be coded for 20 amino acids, and they have different natures. Like they cannot be dissolved in water, and they can be dissolved in water. They are acidic, they are just basic. So how are you going to deal with that problem? I want to know that.
Yeah, that's a really good question. So there are like some changes I can make within the speciation software WORM to try to get it a little bit closer to Titan's system, but it was really designed for Earth, and so there's limitations to what I can do there. As far as the amino acids themselves, once I have broken them apart, the idea is that like a bucket of Legos, you can build like many different things out of them without it necessarily being geochemically specific, and rather, once we have this final product, we test whether or not it could actually exist in that environment. So like the building process itself, on the pipeline, it starts to get complicated like right about here once we get to specific systems. But up until that point, it should be agnostic.
Okay, thank you. And this is not a question, but I want to just give you an idea that there are 20 essential amino acids. So there are only 20 amino acids there that have been discovered so far. So if you can, you just discover some others also.
Perfect. I'll try.
All right, let's give another round of applause. All right, so we're on break from 2:30 to 3 p.m. and then at 3 p.m. we have our next keynote. So be sure to make that because it'll be great. Just a reminder to just remember to say your name and your university when you're asking questions, and then if you're giving a talk tomorrow, just make sure that some of the slides look good before you present. Jennifer, it was not your fault. Sometimes this computer is very mean to people, so just check to make sure your slides look good. All right.
Hello. Welcome back from break, everyone. I hope you all had some coffee, wake up a little bit for our second keynote. Today we have Dr. Jonathan Lunine presenting for us on how I became a scientist and exploration of the solar system's ocean worlds. So Dr. Lunine is the David C. Duncan Professor in Physical Sciences and Chair of the Department of Astronomy here at Cornell, although he just announced that he is now going to be Chief Scientist at JPL starting end of the summer, beginning of the fall. He is interested in how planets form and evolve, what processes maintain and establish habitability, and what kinds of exotic environments might host a kind of chemistry sophisticated enough to be called life. So I'll hand it over to you.
All right. Well, thank you, and it's really a pleasure to be here. I was asked to give an autobiographical talk as well as discuss some science. I always get a little worried about the autobiographical part because my life is not all that exciting. There's a big difference between someone who studies rocks and stars and someone who is a rock star, and sometimes they get confused, but we'll give it a try. Here we go. All right, I was born in 1959 in New York City. I think that's my real hair, but both my parents are dead, so I don't know. And my mother was a rockette at Radio City Music Hall, one of the famous precision tap dancers. My father ran a haberdasher store. I was interested in astronomy from very, very early on. I remember the Golden Book of Astronomy, but most of what stimulated my interest was being so fortunate to be able to live in Manhattan, 7 blocks from the Hayden Planetarium, which is one of the great planetaria in the world. And this is what it looked like when I was growing up. It got completely renovated into something called the Rose Center today. But at that time, it was a brick building with a green dome. And as a little kid, if I could get my mother or my older cousin to take me there, it would just be going into the wonders of the universe. And in particular, in the Sky Theater, you sit in these seats, this Zeiss projector, which could project the brightness and positions of thousands of stars, would rise up from the center of the circular star theater, kind of like some alien creature, and open up the heavens. And in living in Manhattan, you really can't see the stars very well. And so this was the only way that I could do that. And then controlling all of this before the age of the computer was an astronomer. And the astronomer, who at that time was always a male, would stand at this console and operate dials and levers and tour us around the stars. And I thought, wow, this is someone with a lot of power commanding this thing to rise up from the center of the Sky Theater and opening up the heavens. So this really made a big difference, and I was very, very interested in astronomy for that reason. I was also interested in space and science fiction, and so here I am, probably around the age of, 12 maybe, and in my bedroom you can see the lunar module in the background from Apollo, and those pictures to my right are art from the covers of analog science fiction magazines. So I was very interested as well in both space, flight, and science fiction. So Apollo 11 landed on the moon when I was 10 years old. And the later Apollo missions, 15, 16, and 17, were multi-day geological expeditions. It was possible to order from the US government printing office these guidebooks on the moon with Apollo 15 or 16 or 17. They would detail all of the geologic stations and the time there and the various geologic features and the observations and activities. Now, I discovered this after Apollo 15, so I ordered the ones for 16 and 17. And fortunately, we had cable TV in New York City, a very early form of cable TV. And there wasn't very much in the way of programming available for cable TV. So the moon walks for 15, 16, and 17 which pretty much had been abandoned by the networks, were just broadcast without interruption on cable TV. And so I remember sitting up at 2 or 3 in the morning, as it happened to be for, I think, Apollo 16, and following along with the geologic guidebook and feeling like I was really part of those expeditions. So that too made a really big impression on me, the idea that you could even vicariously participate in some of the most astounding adventures that human beings could have, which is to not only walk on the moon, but drive around and do geology and science there. I was also into science fiction. First year of Star Trek, I was too young. It was after my bedtime, but I managed to sneak a glance once, and I was really fascinated, so I was able to watch it in subsequent seasons, and I became a total Trekkie, went to Star Trek conventions. There were some science fiction authors I really loved, Isaac Asimov and Arthur C. Clarke in particular. 2001, A Space Odyssey, the movie was a complete mystery to me, but I read the book and I thought it was great, and I went on to read Childhood's End and The City and the Stars. Those are the original books that I had. I also had a tendency to get a little bit into fantasy and things that perhaps a more skeptical person wouldn't have believed in. I really was captivated by the idea that extraterrestrials had visited the Earth and had made their mark on human civilization. And I was taken in by Erich von Daniken's book, Chariots of the Gods. This is a contemporary picture with one of our 2 dogs, Emmett. Emmett is clearly very disappointed that I would own that book and has positioned himself where that book belongs. It was really a nothing burger, but you know, as a kid, I was taken in by this. Luckily, around that same time, a book came out that was both skeptical and visionary. And that book was The Cosmic Connection, an Extraterrestrial Perspective, written by a Cornell professor named Carl Sagan. This was years before the Cosmos series. And I can't remember how I got wind of this book. I think it was in Sky and Telescope magazine, but I ordered it. It came in the mail several weeks later. There was no Amazon, of course. And I read it. And I was thrilled because the book was at once skeptical and at the same time visionary about the possibility of humankind's destiny being in the cosmos. It was a beautifully written book. And I was so taken by it that I would read it out loud in our apartment. My mother finally said, "Why don't you write to Professor Sagan?" And I thought, well, that's ridiculous. I was first year in high school. You know, he's not going to write back to a high school kid. But my mother was very insistent, and so we always listened to our moms. And I wrote, and he wrote back. And he wrote this letter, April 1974, about how to become an astronomer in great detail. And he also enclosed a couple of reprints from the Mariner 9 mission, which was going on at the time. So I was really thrilled by this. I wrote back. We had exchanges of letters. He remembered that years later. This was really seminal for me because it connected me to a real astronomer, and a real astronomer who was willing to tell me, here's what you should study to become an astronomer. Study physics and math. And you don't have to go to, in fact, it was sort of ironic. He was explaining why Cornell didn't have an undergraduate major in astronomy, and today we have an undergraduate major in astronomy. But he said at the time, you really just need physics and so on. So this was really thrilling for me. And it pointed the way to my being able to be an astronomer. And then I lost courage. Right around that same time, some months later, I wasn't sure I wanted to be an astronomer after all. The reason for that is that at that time, the NASA budget, in fact, the whole research budget of the United States, was declining. And the NASA budget in particular was coming down from a high during the peak of the Apollo development to a value in 1974 that was a factor of 3 times smaller. So if you didn't know what the future held, which of course couldn't at the time, and you looked at this chart, it looked like NASA was going out of business. And The stereotype at the time was that physics or astronomy PhDs were finding careers driving taxicabs, which is an honorable profession. I mean, it's very important. Here's a vintage 1970s view of taxicabs in Manhattan. But I didn't think I could really make it as a taxi driver. So I decided I would instead become a medical doctor. And like Jonas Salk, I would invent some great vaccine or some sort of cure for whatever. So I volunteered at Mount Sinai Hospital as a high school student working for a cancer doctor. That turned out to be mostly writing reprint request cards. So in those days, because you couldn't just go on the internet and get the paper you wanted, doctors in particular would write out all of these requests on little postcards, send them off, and weeks later, there would be a reprint. So I wanted to be a doctor. My pediatrician, who also turned out to have been a Cornell alum, I guess didn't think that that was necessarily the right career for me, because he wrote a letter to me in August of '74, pointing out that there was a talk downtown, sponsored by the Cornell Alumni Association, all about Arecibo Observatory. And the talk was given by Frank Drake, very famous astronomer who really was the inventor, instigator of SETI, and he was giving a talk on the new astronomy that was being done with Arecibo now that the reflector had been resurfaced with not chicken wire, which is what it had originally, or mesh, but a real reflective surface. So I almost said, I'm not interested, I'm going to be a doctor. I went to the talk. I was fascinated. I remember leaving the talk thinking, I don't want to be a medical doctor. I really do want to be an astronomer. So here's another Cornell professor who kind of put me back in the right direction and may have saved many lives who could have suffered from my clumsy medical skills. And years later, 40 years later, in fact, because I was too intimidated as a high school student to talk to Professor Drake at the time of the talk, 40 years later, I had a chance to be with Frank Drake at the 50th anniversary of Arecibo, and I told him the story. He thought it was very funny. He could convince anyone to change their careers, but he was very gracious about it. Sadly, of course, this no longer exists, and the reflector's pretty much destroyed. But at the time, it was doing great science. All right, so my father passed away right around the same time. He was an alcoholic and also a pill abuser. It was very dark times in my family. And actually, Star Trek and Carl Sagan and the Drake talk were things that really kind of kept me going. But by the time I decided to go back to astronomy, things were getting better. My mother remarried. This is my stepfather, Norman Jacobs, who is retired now, an Australian chemist. And so that was going well, and I applied to Cornell, got into Cornell. We couldn't afford it because our finances were just in bad shape, our family finances. But I got a great scholarship from the University of Rochester and had a terrific undergraduate education there. Meliora, if anybody is U of R. Nope. Okay, where's Aiden? So he's from the U of R. So I majored in physics and astronomy, had a great education there. Had a wonderful professor for stellar atmospheres, Hugh Van Horn, who actually got his PhD here at Cornell in the late 1960s. And he team taught it with Judy Pfeiffer, who got her PhD here at Cornell as well. And Hugh Van Horn became my senior thesis advisor. So around the time I took that course, spring of 1979, I still subscribed to Sky and Telescope. The March 1979 issue of Sky and Telescope had this beautiful image of Jupiter taken by Voyager 1 on its way inbound to the encounter with Jupiter. Now, that image is not so impressive today. Juno and all that do much better. But at the time, it was astounding. It was much better than what ground-based telescopes could do. And so when I saw this cover image, I realized that the kind of astronomy I wanted to do was planetary science. And I wanted in particular to participate in spacecraft missions like Voyager. So Hugh was very, very nice about all this. He was not a planetary scientist, but he said he would propose a senior thesis project as close to the planets as possible, which turned out to be doing models of the sun. Pretty close, you know. The planets go around the sun. But Hugh also introduced me to the person that would be my dissertation advisor. I ended up applying to a number of schools. My stepfather encouraged me to go west, so I ended up at Caltech. And David Stevenson, who also got his PhD here at Cornell about 10 years after Hugh Van Horn, had just started at Caltech as a new assistant professor. And Hugh made the contact, and we started working together. And he became my PhD advisor. So it was a very intense 4 years. That's a pretty short time. It was not all smooth. There were some rocky periods. Dave and I nearly had a breakup because I kind of lost focus on what I wanted to do and began spending time doing other things, both in science and outside of science. He wrote me this letter, handwritten letter, 2 pages, and we had a long discussion, and that kind of got me back on track. So I think Dave is retired now. I think his style of mentoring at that time might not be the style that's necessarily the gold standard today, but it really did work for me. And getting over that crisis and having him point out when I was losing focus was really important. This was the most fun project, proposing an ocean of ethane on Titan's surface, which was a motivation for some of the instrument designs for what would become the Cassini and Huygens mission. So I got my PhD. I went to the Lunar and Planetary Lab in Tucson as a postdoc. This is a picture of me around that time, and I'm showing you that picture so that you can compare my face in the picture to my face now. And to just point out to you that in your 20s and 30s, you have much more energy, much more of the things that come with youth, and that's a very important aspect to take advantage of. I mean, here I am smiling with these very sort of, well, I'm not going to attempt to describe it. But anyway, yeah, it goes downhill from there. So that's the main point. But I was a postdoc. This is my mother's third husband. She remarried, although she remained friends with my stepfather for up until her death. So I was postdoc at Lunar and Planetary Lab. I did a little one-term or one-quarter stint as a visiting assistant professor at UCLA, and I applied for faculty positions. And there were a number I didn't get. I didn't get the one at the University of Hawaii or Brown or this or that, but there were 2 offers, and one was from the University of Arizona, and I came back to Tucson. So this is my offer letter. And if you can read it, I want to point out a couple of things. First of all, this salary, actually $29,000, is really good, because in today's dollars, it's over $80,000, which is pretty good for an assistant professor. But I want you to notice the startup package. The startup package, which today is often hundreds of thousands of dollars or $1 million sometimes, guaranteed my first year's summer salary for 3 months. That's pretty standard. And then it gave me operating funds in the amount of $1,000. Wow. Okay, that does not equate to $1 million today. To cover telephone, copying, all the things that we worry about today, right? And travel in the additional amount of $2,000. So, and a personal computer, an IBM PC-AT. Does anyone know what a PC-AT looks like? It's this box with a fan and a TV screen on top. And it goes, and it was pretty cool. All right. So I actually started with a very small startup package. Now, I'm not saying that if you apply for faculty positions and you get a faculty position, you should say, just give me $1,000. But it turned out in my case that because I was so interested in missions, that it really didn't matter, that a lot of the resources that came from NASA were the things that were able to keep me going. Okay. I got married in 1987. My wife, Cynthia Ewing, now Cynthia Lunine, is there. My sister is on my left, and she's a dancer, and our stepfather is there on the right. We have one son, Cynthia and I, who's now living in Philadelphia and is a software engineer. And I just got started proposing for missions. And this is the best list I could come up with for this talk. It's probably not entirely complete, but my point in showing this is, first of all, that you will never get all the missions you propose for. The red ones are the ones that either my proposal was rejected, or the team that I was on was rejected, or the proposal was accepted, but then either the instrument or the mission was canceled. So that was the case for the Comet Rendezvous Penetrator, the Circle camera for the Rosetta Champollion lander. The whole lander was canceled. And Europa Orbiter Ice Pack. So this was 2000. So it has been 24 years, sorry, since people were proposing instruments for Europa missions. That's a very, very long time. Right? And we're within months of a mission actually launching. So the big ones that were important to me, Voyager, Neptune. I was a guest investigator on the ultraviolet spectrometer for the Neptune encounter. Cassini-Huygens has been a big part of my life from the late 80s up through the end of the mission in 2017. James Webb Space Telescope, sorry about that, James Webb Space Telescope right there. As an interdisciplinary scientist, 20 years of development, 20 years of meetings of the science working group. And of course, that telescope went from $1 billion to $10 billion, almost 11. Juno has been a great mission orbiting around Jupiter, and then Europa Clipper and JUICE. So those are kind of the big missions. And in all of this, I don't build instruments. I don't really do data analysis. In my first year in E&M lab at Rochester, I broke a voltmeter and also shocked my lab partner. He was okay. So I've been a theorist, and I've been able to work on these missions in roles like interdisciplinary scientist or co-I responsible for planning and development of the science concepts that would then lead to the building of those instruments, and then participating in the data analysis and the theory that goes on behind it. So that's really how my career has gone, and it's worked out pretty well. In 2007, after thinking about this for a very long time, I grew up in a Jewish family. I was baptized and confirmed in the Catholic Church at the Newman Center at the University of Arizona, where I was a professor. I'm not saying that you should do that as part of your career. This was something that I had been thinking about for a very long time, and realized that my own personal and spiritual beliefs aligned with Christianity. And since that time, I've pursued work on science and faith, the question of the conflict between science and faith. Is it real? Is it not? The harmony between science and faith. I've helped to start a few organizations. I've given a lot of talks, and this has been very enriching for me and for some of the students and others I've worked with. But it's also, I think, for me personally, when I did convert, I was very worried that many of my friends who are Jewish would reject me. And that turned out absolutely not to be the case. And so it was a really wonderful thing to realize that friends who really are friends will be your friend regardless of how you change. And that was a wonderful thing to realize. So academically, this has been my journey. I started out at Rochester, went to Caltech, got my PhD there, went to the University of Arizona, taught there for 25 years, thought we would stay forever. We loved Tucson, but I got tired of some of the politics associated with the state, and also the politics of being at a state university and watching ASU, for those of you who were Sun Devils, kind of grow and overshadow the U of A. During 2 sabbaticals and many summers, my wife and I came to love Italy, made many friends there. Our son didn't like it quite so much. But around 2008, I applied for a 3-year teaching position and was able to negotiate a leave of absence from the U of A to go teach at the University of Rome, Tor Vergata. This turned out in the end to be a real disaster because of Berlusconi was the prime minister at the time. The education minister was in there really to get rid of higher education, as far as I could tell. There were strikes by the younger researchers. It was really a mess. But in the middle of this, around 2010, Jim Bell, who had been here at Cornell, moved to Arizona State University. I have nothing against Sun Devils, by the way. I think it's a great place. So he moved to ASU, and that left an empty position at Cornell. And a colleague of mine called me up and asked if I would be interested potentially in coming to Cornell. So I said goodbye to Rome and said goodbye to the University of Arizona. Everyone was very gracious there, and moved to Cornell in 2011 with my family. Been here for 13 years, had a wonderful, wonderful time. Have been the director of the Cornell Center for Astrophysics and Planetary Science, department chair. And then an opportunity has come up in a place where I have done most of my scientific research over 40 years, and that's Jet Propulsion Laboratory, to help guide their science and develop strategic plans at a time when science is not doing all that well in NASA compared to other things. So I agreed to do that, and so it's back up to Pasadena, California. I don't have any intention of going around this game board again. Once around is enough, and then I will retire. So I wanted to talk briefly about mentors. Mentors are really important, and these are some of the ones that I've had over time. So Carl Sagan inspired me and showed me that I could be a scientist. Hugh Van Horn was the best professor I had at Rochester and introduced me to my thesis advisor, David Stevenson, who I thought was really a great thesis advisor despite some of our ups and downs. Don Hunton, who's passed away now, was my postdoc advisor at Arizona, and both Dave and Don plugged me into studies for the Cassini mission that were going on during the 1980s that enabled me to then write proposals that allowed me to get onto first the Huygens part and then the Cassini part of the mission. Charles Alachi at JPL got me involved in discussions about what you could do with a radar system on Saturn's moon Titan, and that eventually led to my being on the radar team for Cassini. But it was Angeletta Corradini, who was my best friend in Italy, who had a lot of influences on me. I met her when I was still a graduate student. She also plugged me into studies for Cassini and invited me to conferences that were relevant to this. And then she arranged for our sabbaticals, and even until she got into a big fight with the people above her, was going to groom me to be the next director of the institute that she was running. Angeletta was the director of 2 institutes of space astrophysics in Italy, which at the time was very unusual. Italy is behind the United States in terms of diversity and opportunity. She was one of only 2 women who directed a research institute in the 90s and 00s, passed away from cancer in 2011. But the thing that I remember most about Angeletta is she was the one who was willing to tell me what my flaws were, which as a mentor is really essential, but can be done in a really bad way or a really good way. And she managed to do it in a really good way. She showed me, told me what my kryptonite was. And unfortunately, I learned about this too late to kind of correct some of the things that had happened earlier in my career that were part of this personality defect. But once she told me about it, it was something that I've worked on for a long time after that. So she's the one I'm really most grateful to, and unfortunately is no longer with us. So what can we learn from this part of the talk? Mentors are super important, and being a mentor is a great responsibility, and most of us are not as good at it as we could be because we're not well trained. So training of mentors is super important. And now the National Science Foundation requires proposals, PIs on proposals, to write out a mentoring plan for their students and to give progress reports on that every year of the proposal, and it's something that NASA should do as well. Graduate school, I don't need to tell you this, it's pivotal. Habits are formed when you are a graduate student. Focus is important. I lost focus halfway through grad school. Luckily, my advisor pulled me back. Passion for what you're doing is super important because we're not in the highest paid jobs in the world, to be honest, compared to finance, so please do make the most of it. And here's that point. You really are at your intellectual and physical best in your 20s and 30s. So that's a good time to take those risks that will allow you to really find your strengths and your weaknesses, and to recognize that while we kind of grow in wisdom after that, wisdom doesn't really trump some of the advantages of youth. And there are twists and turns in life. To the extent that you can, take advantage of them. I love this quote by Girolamo Cardano, who was a 16th century doctor and kind of a Renaissance person. And he wrote at the end of his autobiography a year before he died that one should live cheerfully and good in the exercise of some art in which one is skilled. And what we're doing in science is the art which we are all skilled in here. So I want to move on in the last 20 minutes of the talk to the search for life in the outer solar system. And I want to focus on 3 objects that have the best evidence for liquids either on their surfaces or in their interiors. Jupiter's moon Europa, Saturn's moon Enceladus, Saturn's moon Titan. All 3 have oceans under their surfaces. In the case of Europa and Enceladus, there are multiple lines of evidence for those oceans. In the case of Titan, it's a little shakier, and that ocean is very deep down. But Titan has another kind of liquid methane and ethane, covering 1% of its surface, and that makes it a very, very intriguing place. So let's start with Europa, and I recognize that some of you who are working on these objects know this stuff, so please chime in the question period, or now if you want. So Jupiter's moon Europa is the size of our own moon. It's a mostly rocky world, has a density of 3 grams per cubic centimeter. It has a very tenuous atmosphere. It's embedded in a very intense radiation field of Jupiter that makes it extremely hard to explore Europa, even with robotic spacecraft. And it has a subsurface water ocean under an ice crust that has very few craters on it, so that it's evidently a very young and active surface. And this image from Galileo shows a region where the ice has been broken apart and rotated over what must have been at the time of that rotation a liquid, a water liquid, ice floating on water. So the Galileo probe actually discovered that that water is in existence today. I'll explain briefly in a moment how that's known. Given the density of Europa, and given then the amount of ice that can be present, given that the liquid is somewhere, can't be too far below the surface, one can do a model of Europa that demonstrates that the amount of water, liquid water in Europa, is somewhere between the amount that's on the Earth, that's this little drop here, up to about twice that. So Europa's ocean is between 1 and 2 times the volume of the Earth's ocean, which is extraordinary because it makes for a lot of space for whales, for sure. But the question is, are there whales? Are there any organic molecules of any kind at all? And that's been the difficulty in understanding that ocean. So this is kind of a model. The other important thing about Europa, as opposed to Ganymede and Callisto, which also have oceans, is that because Europa is mostly rocky and actually doesn't have that much water, ice, and liquid water, the base of the ocean is at a pressure that's below the pressure at which high-pressure ices of water become stable. And so the contact between the rock and the liquid water ocean is not interrupted by high pressure ices the way it would be on Ganymede or on Callisto or even on Titan. And that means that minerals that are leached from the rock are accessible to any organisms that might be present in that ocean. So that makes Europa very special among the Galilean moons. So the way that this ocean was really discovered came from the Galileo magnetometer. Jupiter's magnetic field axis is tilted relative to its rotation axis. So if you look at if you're in the plane of Europa's orbit, which is this green line here, what you see is the magnetic field lines bobbing up and down relative to the plane of the orbit. And if you look at that image long enough, you see those field lines bobbing up and down. So from the point of view of a conductor in Europa's orbit, two things are happening. One is the field is moving at the rotation speed of Jupiter, so it's sweeping through the body, whether it's a conductor or an insulator. And number two, there is a time-varying magnetic field because of this bobbing, which, if this body is a conductor in orbit around Europa, generates eddy currents, which then generate an induced magnetic field. And it was the induced magnetic field that the Galileo orbiter in 1997 and 8 detected during several flybys of Europa. And the geometry of that field and its strength required that it not be deep down in an iron core, which Europa probably doesn't have anyway, but rather had to be near the surface and something like the conductivity of slightly salty water. So that was really the slam dunk for an ocean underneath the surface of Europa. And it was remarkable because it was one of the few things that the Galileo orbiter, which had a damaged antenna and a broken tape recorder, could really do. It couldn't make very many images because of problems associated with its launch and deployment. All right, so the question then is, are there signatures of the ocean on the surface of Europa? And that is the big question. There are a lot of brown stains on this icy surface. A lot of that is probably stuff from Io, nearby Io, that has been deposited, sulfur deposits, magnesium salts, and so on, that are then radiation darkened. But there's also indications of other things. This image was not taken by Galileo. This was taken by the Juno spacecraft in a flyby of Europa a couple of years ago. The camera, the Stellar Reference Unit, is actually an engineering camera designed to take pictures at low light levels of stars in the background of Jupiter so that engineers can determine the orientation of the spacecraft. But it's also a great geology camera. And this image was taken when the sun was on the other side of Europa. The imaging, the light was Jupiter shines. This is taken in Jupiter shine. And what you see here is an area of Europa that is crisscrossed by lots of different fractures and has this very curious feature here, which informally we call the platypus. And if you stare at it long enough, you can see that it really is a platypus with the eyes and the beak and the body there. So Heidi Becker at JPL is the principal investigator of the science component of the Juno SRU and led a paper which we published earlier this year. This was a lot of fun. Because this feature was also imaged at poor resolution by Galileo in the 1990s at a different angle, it was possible to put together a stereo image. It was possible to put together topography. And it turns out that this part of the platypus is slightly domed. And that allowed us to distinguish between various models. And the model that fits the formation of this feature best is one that was published by Brittany Schmidt about 13 years ago, in which you have a warm region that comes up to the surface, melts a mixture of ice and salt, a brine essentially. That causes the feature to collapse, and then as it refreezes, the expansion causes the center of it to dome up. And that fits this thing very, very well. So this is evidence, and there are other features like this, of liquid water and salt melting in the crust. The other thing you see here up in this region is a fracture with these dark stains on it. And that's very similar to a feature that Galileo imaged elsewhere on Europa and was analyzed by Lene Quick at Goddard Space Flight Center and Matt Hedman as being the deposits from little plumes that are along this axis and depositing this material, which is then radiation darkened. So what is the material that's actually contributing to that radiation darkening? Well, it turns out that Europa has been a great target for Hubble Space Telescope and James Webb Space Telescope. In 2019, Samantha Trumbo and colleagues, Samantha was a graduate student at Caltech at that time. She's been a 51 Peg B postdoctoral fellow here at Cornell and is now on her way to San Diego in a faculty position. They mapped salt, sodium chloride, spectroscopically on Europa's surface and saw that it correlated geographically with those chaos features, that chaos terrain with all of those crisscrossing lines and features like the platypus. So sodium chloride could be from Io, but why would it be geographically located like this? It looks like something from the interior. What pointed to this really coming from the interior was that when the Webb telescope was launched, it was able to look in the infrared and map carbon dioxide on Europa's surface. And carbon dioxide also is correlated with those same chaos features. The thinnest part of the crust, the most heavily fractured, the most likely places where the ocean is going to be coming out onto the surface. So in two papers, Trumbo and Brown, and another led by Geronimo Villanueva, the CO2 data were published. And it really looks like the ocean is in contact with the surface and produces carbon dioxide and salt from its interior. So does it have organics? And where in detail are those places located? Well, that's the role of Europa Clipper, the mission that will be launched in October. Clipper will orbit Jupiter and make 50 flybys of Europa, and that way the radiation dose is minimized relative to if you were to orbit Europa itself. And Europa Clipper is extremely well instrumented. It has 2 mass spectrometers. It has ultraviolet, visible, and near-infrared cameras and spectrometers. It has a thermal infrared bolometer for detecting hotspots. There's a radar that Professor Schmidt's involved in that will hopefully penetrate to the ocean. And then it has a much better magnetometer and plasma measuring device than Galileo, which will get the salinity, the conductivity, and therefore the salinity of the ocean much more precisely than Galileo could. And then gravity will get the overall structure. So it'll be launched hopefully in October, fingers crossed. A mission called JUICE, Jupiter Icy Moon Explorer, is already on its way, built by the European Space Agency. Its main focus is Ganymede and Callisto, but it will do a couple of flybys of Europa and hopefully contribute to those investigations. So let me move on to Enceladus. Enceladus is a surprising object because it's so small. It's a moon of Saturn, 500 kilometers across. It turns out to be, as you learned in the keynote address by Morgan Cable on, what are we, Tuesday night, Monday night? Monday night, okay, I got second guess, good. So you learned all about it there. I'm not going to review that. It has this marvelous plume which material is pouring out. The Cassini spacecraft, the Cassini Saturn orbiter, carried 2 mass spectrometers and was able to fly through that plume, which it discovered, and make measurements of the composition of the ice and the gas. And by doing that, it demonstrated that this material was really from the ocean, and then by making other kinds of measurements of the libration of Enceladus in particular, demonstrated that there really is a global ocean of liquid water. So one of the things I want to focus on is the potential for life. And in a paper by Hunter Waite and colleagues in 2017, Chris Glein at SWRI in the supplement portion did a remarkable calculation in which he took the data from the mass spectrometers, which showed the abundance of carbon dioxide, methane, water, and hydrogen, as Morgan talked about. And he assumed that these were related to each other through a process that's called methanogenesis, that carbon dioxide and hydrogen were making methane. Furthermore, it was possible to constrain the pH, the acidity of the ocean, because chlorine and other components of salts were also measured by Cassini. So it was possible for Chris to put together a plot of what's called the affinity, chemical affinity, which is the departure from equilibrium, assuming that this reaction occurs, or set of reactions that are summarized here, versus the amount of hydrogen that's present in the ocean. And these lines are lines of constant pH, assuming this reaction is relevant. So if you plot where the Cassini data lie, they're in the blue here, constrained by the pH and constrained by the hydrogen mixing ratio. And that's a significant departure from equilibrium. The affinity is 0 if the ocean is in equilibrium, if the CO2 and methane and hydrogen abundances are what you would expect in thermodynamic equilibrium. But they're not. So you say, aha, potential for life. Yes, but most life on the Earth keeps its environment close to thermodynamic equilibrium. Basically, if you walk into a pizza shop and there are lots of uneaten pizzas there, you assume that there are no human beings there to eat the pizza, and you go ahead and you consume it, bringing the pizza shop close to equilibrium. In this case, this is a little suspicious, but in fact, as Tori Holer pointed out in 2022, there are terrestrial ecosystems, microbes, which can't keep their environment close to equilibrium because they're limited by the nutrients. They're limited by the amount of hydrogen or something else. And so this blue box actually sits pretty comfortably in the range that terrestrial ecosystems that have methanogenesis in them actually lie. And so it's possible that indeed there is life in the ocean of Enceladus generating methane from carbon dioxide. So how do we find out? Well, one way is to go back with better mass spectrometers. So the Cassini mass spectrometer, the INMS, one of the two, had a mass resolution that could only tell you whether you were seeing something of mass 28 or 29 or 30. In other words, unitary masses. So if you had a mass 28, which Cassini did, you couldn't tell whether you had carbon monoxide or nitrogen or ethylene. They all have mass of 28. But modern mass spectrometers that can be flown in space, like MassSpecs, which is on its way to Europa, get 100 times that resolution. And so they can see the fractional masses associated with the binding energy of these atoms in the molecule. The binding energy takes away mass from the atoms, and so you end up with what's called a mass defect. And that's different for carbon monoxide than it is for nitrogen, than it is from ethylene, C2H4. And so you can distinguish between all these molecules. And just flying this through the plume of Enceladus would remove a huge number of ambiguities and allow us to say what the composition is and even whether there are amino acids present. So Kelly Miller is the principal investigator for mass specs for our Enceladus mission that we've been proposing. And also the other mass spectrometer, the mass spectrometer for the solids on Cassini was able to tell us that there are some sort of heavy organics there, as Morgan pointed out, but not the identity of those. And so flying something with much higher mass resolution will get us the identity of these heavy organics. And furthermore, with today's technology, you can go out to much higher masses, the mass range where, in fact, biological molecules, heavy amino acids, dipeptides, peptides, fatty acids, et cetera, would be present. So this is what we want to do. We want to be able to measure amino acid and fatty acid abundances and distinguish between the biotic and abiotic abundance patterns. So far, it's been difficult to convince NASA to do this, but we're all going to give it another try. And Morgan Cable is one of the key people on this mission proposal. Beyond that, landing on Enceladus is in the Enceladus Orbilander concept that was proposed for the decadal survey that was led by Shannon McKenzie at APL, would be a way of collecting even more material than you could collect from the plume. All right, so let me finish with Titan. So I'll be 5 minutes over, I apologize. All right, so Titan is enormous, right? I mean, if you looked at Titan, if you had something like this in the sky over Ithaca or New York or wherever, you'd say, whoa, what did I eat? Or what did I take? It's larger than the planet Mercury. It has a dense atmosphere, 95% nitrogen, the rest is methane. Earth has a nitrogen atmosphere, the rest is oxygen. In the case of the Earth, water is the meteorological fluid that creates clouds and rain and rivers and ice. Turns out on Titan, because it's so far from the sun at Saturn and so cold, methane does exactly the same thing, plays the same roles. But the difference is that methane is the starting point for a rich organic chemistry. So high in the atmosphere of Titan, the density of the air at Titan's surface is 4 times denser than the air in this room. So ultraviolet light or cosmic rays really don't get down to the surface. Few cosmic rays do. But high in the atmosphere, ultraviolet light can break up methane to form acetylene, ethane, and then a whole series of other hydrocarbons. And because nitrogen is present, the nitrogen can participate as well, making hydrogen cyanide, and that's the starting point for a whole suite of nitriles and imines. And so there is this rich organic chemistry that is known in Titan's atmosphere, but not so well known yet on the surface. These are all less volatile than methane, so they condense out and rain out onto the surface. The methane and the ethane are liquid at Titan's surface temperatures of 94 Kelvin. And evidence for methane liquid is found at all scales from the Cassini-Huygens mission. From the Huygens probe descending by parachute, these 3 images put together show a dendritic feature on a hillside, presumably carved by methane. And when the Huygens probe landed on the surface nearby, out in this region, because the bottom of it was warm and the mass spectrometer inlet was heated, methane began pouring out of the surface, methane and ethane. So there is methane and ethane soaking the soil and carving these features. On hundreds of kilometer scales, lakes and seas, discovered both by imaging and by radar. Titan's atmosphere is hazy, so radar really gives you the clearest images. This is Ligeia Mare, 500 kilometers across, which makes it as big as Enceladus is in total. Shows you how small Enceladus is. And the Cassini radar was able to detect not only this feature, which is very smooth and very dark in radar, but it could detect both the reflection from the top and the reflection from the bottom of the sea. The time delay between the two gives you the depth, so there's bathymetry for these seas, and the attenuation of the signal from the bottom relative to the top then gives you the composition using laboratory data, and that composition is methane and ethane. So now we know, thanks to Cassini and lab data, that these are methane-ethane seas. And then finally, on the very largest scales, seasonally, when Titan reaches equinox, there's large-scale rainfall in the equatorial regions which darken the surface on scales of thousands of kilometers, and that is presumably due to methane as well. So what is going on the surface? Well, that we know very little about. The Cassini-Huygens mass spectrometer could only tell us a limited amount. But laboratory experiments show some very intriguing directions that, in fact, the organic chemistry on Titan could involve further evolution on the surface. So liquid ethane combined with benzene can produce what's called a co-crystal. And in some work by Vu Cable and colleagues, they show that this is what would happen as the ethane, as the lake dries up, and what's left behind includes these sorts of co-crystals. So they, in a later paper by Morgan Cable and colleagues, postulate an entire organic mineralogy on the surface that is based on association of different organic molecules with each other. And this is totally different from anything we have on the Earth. And it begs the question, where does chemical evolution end on Titan's surface? Titan's surface has diverse energy sources. It has long temporal and large spatial scales. It has a chemically rich surface where life as we know it can't exist. There is no liquid water, and so the chemistry is unimpeded by biology. Now, in a paper led by Mike Wong in 2023, exploring the question of why the universe seems to evolve toward ever more complex and information-rich structures, they pointed out, and it's Mike Wong here in the audience, that, the laws of physics that we have are all-time symmetric, except for the second law of thermodynamics. And the second law of thermodynamics doesn't tell you why systems become more complex and more information-rich. So they postulated a missing law, which is called the law of increasing functional information, which certainly is applicable to biology and even mineralogy on the Earth, because minerals have evolved with time, and maybe is applicable to all complex systems that have access to lots of energy and lots of time. So Titan's surface is a great place to test this idea, to see whether the abundances of species that are on the surface do or don't obey the simple laws of chemistry, to look for things that are not defined in their abundance by simply free energy of formation, but rather by this tendency for systems to evolve toward ever more complex structures. So for example, if we find graphene on the surface of Titan rather than cyanoacetylene, graphene is an excellent storage molecule for hydrogen and would be a way for Titan's surface and atmosphere to continue to reconstitute the methane that's been destroyed in the upper atmosphere. So how are we going to find these molecules? What are we going to do? Well, flying a dual quadcopter or flying rover, or however you want to call it, is the way to do it. So this is Dragonfly, which is being developed by APL for launch to Titan in 2028. It has a chemical analysis system where material is brought in by literally a vacuum cleaner, because there's air on Titan, so you can have a vacuum cleaner. Zibby Turtle is the mission PI, and this potentially could detect through its mass spectrometer the kinds of molecules that would be part of Titan mineralogy and maybe even part of an increasingly complex functional chemical system in the absence of life itself. All right, I want to just close now by pointing out one more mission and one more place to go. The Uranus system has 5 moons, 3 of which may be, has 5 moons, 2 or 3 of which may be ocean worlds. We don't know. Voyager 2 didn't get a great look at those moons. But the Uranus Orbiter Probe mission came out of the Planetary Decadal Survey, which you heard about earlier this week from Morgan, as the highest priority mission after Mars sample return. And I was the panel chair for the panel that recommended this mission. The secret to being a good panel chair is to have a superb panel vice chair, who in this case was Amy Simon, and she was the science champion for this mission and really carried the ball all the way. And the vice chairs in the panels were actually on the steering committee as well, whereas the chairs were not, which was an interesting and good way to do things. So this is beyond my time horizon, like the late 2040s, but it's an opportunity to explore a completely new kind of planet that we haven't explored well with spacecraft, an ice giant. And I think that the surprises that will be found are things that, as with earlier planetary exploration, we just cannot predict. Thank you. So I know some of you have to set up your lightning talk, so please feel free to leave if you have to do that. Don't worry about that.
I'll actually start with the questions. Hi, Alexia Kubis, Cornell. I had a science question actually about the platypus chaos feature. You mentioned that you think that's a thin region of the ice shell. I was wondering if you could just expand upon why we think that, because I would think just with tidal heat dissipation and rotational dynamics, I would expect like the poles to maybe be thinner.
Yeah, so that's, of course, a speculation. Don't know if it's thinner area, but the platypus is located in a region where there is a very large number of fractures and ridges that look very, very young. And so that's an area that can be contrasted with, for example, the area where the one big crater on Europa is, Pwyll, Pwyll. And that has to be an area of very thick crust because the crater itself is, I think, 30 kilometers across and has to be maintained. So we don't see craters like that in those heavily fractured areas. So presumably the crust is thinner than it is over in the one place that has craters. Now, whether that's the thinnest area, I don't really know. But what is interesting is that it's an area where there appears to be these sooty things, these smudgy things that have come out of the fractures, which presumably were organics or salts that were then deposited on the surface and radiation darkened. So those had to come out of some sort of liquid if they were from a plume. And that also suggests a relatively thin area where the heat has either liquefied the crust itself or the ocean is actually under there. But we won't know the answer to that until Europa Clipper. So you could be right, it could be the poles are the thinnest, but that's something that Europa Clipper will definitely tell us. And it's super important to understand that if we're going to go back with a lander to look for biology.
Great, thank you. Are there, okay, you have a microphone.
Hi, sir. I'm Shekhar, a postdoc from George Washington University, and also I am a professor in India, assistant professor. So as being a professor, my question is like, first of all, very motivational and inspirational and knowledgeable talk that was. And my question is like, you, in your early phases of like job, you might have faced some institutional competitions, like sort of things. So how did, I want just an advice for that, because for science I can talk in personal outside, but for that I want to know that if you want to give any advice, like how to face these institutional competitions and the patent preservations.
Right, so the question is about institutional competition at a time before you actually have tenure. Competition within a department, for example. So I was very fortunate to be at an institution, the Lunar and Planetary Lab of the University of Arizona, which was not cutthroat. In other words, they hired faculty with the intention that those faculty would gain tenure after 6 or 7 years. And there wasn't a sense of trying to weed out faculty. And, you know, in the United States, Harvard has been the classic example of places where, you know, people don't get tenure. They won't give you tenure unless you're the best of the best. Carl Sagan was an assistant professor at Harvard and didn't get tenure, and that's why he ended up at Cornell. But I wasn't in a place like that, and so I felt that I was being well supported as a professor. However, I had a colleague who came in a year before me, Carolyn Porco, very famous planetary scientist, team leader for the Cassini imaging team. And she was also an assistant professor. And she didn't feel supported because she was a woman and the faculty, with one exception, were all men. And looking back at it, you could see that she was not supported, that it was a tougher environment for her. So she decided she could best do her science from a private entity, Space Science Institute, and so she left. And so today, the intent and the goal should always be to support everyone, regardless of their identity. What's important is that they are human beings doing science and teaching. And you know, I look back at that time and realize that the support that I got was not universally applied to others, in particular my good friend who was just a year ahead of me in the whole process. So I don't know how that applies to India, because I don't know India very well.
No, it
but I
actually
hope
applies, or I'll try here although. Thank you so much.
You're welcome.
Thank you. Hi, I'm Adesh from Georgia Tech. I'm a graduate student, just joined Georgia Tech. So I had two questions, one non-science and one science, but I'll go to the non-science question first. You said that, well, graduate school is like really the pivotal point in like any any person's like who's like a graduate student at this point. It'll be their pivotal point in their career. So you also said that it ebbs and flows. So like, how do you deal with like days when you just don't feel like going to the lab or like working?
Right, right, yeah. So when I was a graduate student, there was a period when I had too many of those days, and I ended up just like going to the weight room, for example, when I should have been at colloquia and seminars. That was one of the things that I kind of got criticized for. But you have to, I think, that was a particular circumstance. So there will be days when you have normal burnout and you don't feel like working, and you just accept that you don't feel like working, and you let people know that and say, I just need a self-care day. And that's okay, because by and large today, and you can contradict me if this is not true, I think that faculty and research supervisors are more sensitive to that than they were 20 or 30 years ago. At least I hope so. If you get to the point, though, where you really feel like you just can't go in, where days go by and you're really stuck, then it's time to try to get some kind of help. And most universities in the United States, there's student health services, which can be helpful. There are friends. If you have a good relationship with your mentor, you can talk to your mentor. But the important point is to be honest with yourself and recognize when you're really beyond the point of just having a bad day and you need to do something to cure yourself, to take care of yourself. That's not an easy thing to do. I mean, a lot of times we don't realize when we're depressed or run down in some way that's pretty serious. So having friends who are willing to let you know that that's the case, that's important too. People who can look at you and say, hey, what's going on? So friends are super important in grad school, and understanding mentors. And if your mentor is not understanding and there are other mentors, think about going to them.
Okay, thank you. That was really insightful. So the second question is, I assume all of these missions that you talked about, this is dynamic in nature. So the objectives of those missions will change over time as you discover more and more data. So how does that work out? What is the pipeline for if you have some data from one of those missions? How does that change the perspective for the next, flyby or something?
Right, that's very good. Okay, so the question is about the dynamics of the missions and the fact, how do you account for what you've learned from, let's say, a previous flyby for the next flyby? And it really depends upon how versatile the mission is. So Cassini orbiter, part of the Cassini-Huygens mission, was very, very flexible. You could change the orbit by adjusting the way that the spacecraft flew by Titan, and that would change the orbit. So in that case, there would be meetings of the project science group and the instrument teams to evaluate what was learned and use that to plan not necessarily the next flyby, but 5 or 10 flybys of Titan further on down. Not just for exploring Titan, but for example, for going into the plume of Enceladus. So when the plume was discovered by Cassini, by the imaging instrument and the magnetometer in 2004 and 2005, the project science group immediately formed a Tiger team to answer the question, how close could you fly to Enceladus? How deep in the plume could you fly without wiping out the spacecraft from the particulates in the plume? And that required doing more remote sensing from Cassini to model the size distribution from the scattering of light. And it required the engineers to say what was the maximum size particle that could hit the spacecraft without damage. And that took about a year. And after that, it was determined, yeah, you could fly, started out at 100 kilometers and then worked down in subsequent flybys to 49 kilometers. So I guess the lesson in that is having a big team and having a very flexible spacecraft, which really means a flagship mission, gives you the most flexibility. Missions that are more focused, more limited, have a smaller mission team, there's less ability to respond to discoveries in the same way. And I think Cassini was the apex. I mean, it would make discoveries and then follow up on those discoveries in the way that I described. You're welcome.
Maybe?
Thank you so much for your
Sure.
talk. Lily Robinthal, University of Arizona, LPL.
Oh.
I am curious what your highest priorities are going into your role now at JPL, and then what science you're most excited about.
Okay, great. So question was, what are my highest priorities going in as chief scientist? So the nice thing about this position is it's not a line management position. I don't have to manage departments of scientists. It's really a strategic planning position. And right now, my view is that JPL's relationship to NASA, to universities and so forth, is not as good as it could be, particularly to NASA. So really high priority is trying to reestablish those good relationships that JPL has had at times in the past. It's a national resource. Even though there are other places that fly planetary missions, they all have their own particular skills, and JPL's ability to land spacecraft on Mars, for example, rove around, do things like that, really is unparalleled. So being able to rebuild that trust is very, very important. And as far as which science is really interesting, so of course I'm a planetary scientist, but I have to say that I've been involved in astronomy and astrophysics. I have some time on James Webb Space Telescope. Of course, as we all are, I've been concerned about the environment of our home planet. And I actually did a little bit of work, some papers on stratosphere-troposphere exchange with Don Hunton, and I wrote a textbook on the Earth. So I have a pretty broad view of what's interesting. What I'm actually looking forward to is learning about science that I haven't had a chance to focus on, and getting really interested and excited in those areas, and to be able to represent and articulate those areas as well as planetary science. Welcome, thank you.
All right, I have a question, so I'm going to step
Yes.
on this side of the mic now. In reference to the first part of your talk, more of your journey and how you got here, do you have any advice for us that are kind of finishing our graduate career but are unclear of what step to take next, particularly academia or industry?
Sure. So in my particular case, I was very sure what I wanted to do. So I don't have the experience of being unsure. I really wanted to go into academia. But I've had graduate students who have gone into industry as well and have made that decision at times almost at the last minute. I mean, I had a graduate student who graduated in 2016 who had a job offer at JPL as an exoplanet postdoctoral fellow and had a job offer at JP Morgan. So for him, it was JPL or JPM. And he picked JPM, but he picked it almost at the last minute. So I think the advice that I would give is if you're unsure of what you want to do after grad school, just plan on applying to different kinds of jobs, just the way that my student did, Don Wang. And you can, coming out of your dissertation, you can apply to postdoctoral positions, you can apply to industry at the same time. You don't have to apply to just one kind of thing. And so that's one way to do it, is just to hedge your bets the way that he did. And if you're unsure whether it's going to be academic or research center or industry, just apply to jobs in all of those. If you want to be able to plan ahead a little bit more, then depending upon whether you're 2 years out from finishing or 1 year out, you should start talking to people in those different kinds of areas. You should reach out to people in industry who have PhDs in astronomy or something else. And very often your mentor or another faculty member in the department will know people, will have contacts that will allow you to make those connections. And then really just talk to them about what those careers are like. And most people are very interested in talking about what they're doing and what their job is like. And so definitely, if you've got a little bit of time, plan on reaching out for people in industry, in academia, and find out what their experiences are like, and that may help you to make your decision. And don't be afraid of the fact that you're uncertain about it, because oftentimes the most rewarding things come out of the most uncertain times in life, either in research or in just life itself. I mean, that happened with the whole Italy thing, which turned out for us to be kind of a disaster, and so I ended up here. So, don't be afraid of those uncertainties, but information is power, so be sure to talk to people in those different kinds of fields. Hope that's helpful. Okay.
One. So I love the way you ended this talk. This was really cool. And when I did AbGradCon in the proposal writing retreat last year, I wrote about like a geochemical investigation of Uranus's moons. And I think it seemed cool because it felt like something that, wouldn't necessarily get a lot of funding in real life. So this question, quick one, inspired by Veronica. She asked this to our group. It sparked a heated discussion. What do you think is the most overrated and underrated ocean world or potential ocean world?
Ooh.
I think we would all like to know, and then I'll hand it off
Ooh,
to Abby.
The most, okay. So probably it's easier maybe to start with the most overrated. I think it's going to turn out that Triton is going to be the most overrated ocean world, because I think that we're going to find that that ocean is sandwiched between layers of high pressure ice at the bottom and, of course, the ice at the top. That doesn't matter. But once you have ice intervening between the ocean and the silicate, then you have a tough time getting nutrients to organisms. That's true for Titan, of course. Titan wouldn't be interesting at all if it didn't have these methane lakes and seas. The ocean itself is not so interesting. And Triton is like just on the boundary of this, depending on how you model it. So that's what I'm going to, oh, are you working on Triton? No, I just love Triton. Oh, I love Triton too. I mean, Voyager, that was the Triton part of the Voyager-Neptune encounter was what I worked on. But Pluto's not underrated because Pluto is less massive than Triton, and so its ocean might in fact be in contact with rocks. So that is all good. The most underrated, that's really hard to, for a long time Enceladus was underrated. People were saying, oh, it's too small, there's not enough, it can't circulate nutrients, it's just sort of a dead world. And I think when the phosphates were discovered in the Cassini data recently and published by Postberg et al., people began to change their minds on that. And then I would just say that I think the Uranian moons are perhaps not underrated but neglected, and if we do get to Uranus with the Uranus Orbiter probe, we're going to find out that there are really ocean worlds there. So, and I want to apologize to Triton and all Triton files because I love Triton too, but you put me on the spot, so yeah, okay, all right.
Hi, Abby Deering, Georgia Tech. I just wanted to ask you about outreach and science communication experiences that, you've obviously benefited from, but things that you're participating in or things that you might recommend that we as early career scientists might want to participate in.
Yeah, the answer is I don't really know. In terms of programs that are available today. I'm not actually the world's best speaker, and I have myself tried to improve by taking singing lessons, for example, which really does help in terms of voice control. And your graduate programs may have courses in public speaking. I know we had that at Caltech. But in terms of actual outreach programs that you could sign up for, I have to say I don't know. But you should definitely talk to some of the people across the way in the OPAG meeting, because NASA undoubtedly has some. So I'm really sorry, but I just have to be honest and say, I don't know. Okay, all right.
I'm Sam.
Hi, Sam.
University of Minnesota. So I've never led or proposed a NASA space mission, but I imagine it involves a lot of talking. Is sense that you have a lot to make, a lot of very complicated, very high-stakes decisions. You have a lot of people involved with different backgrounds. My question is, do you have any suggestions for how to lead productive meetings in those situations where you have to make high-stakes, complicated decisions with a lot of people involved? You had this list of all the proposed projects and the projects that actually happen you're involved in.
Yes.
And I see decades of meetings happening.
Yes, absolutely, absolutely. Right, okay. So first and foremost, I would say it's a really important skill to be able to lead meetings, and it's related to this outreach question as well. Oh, hi, yeah. What was your name? Abby. So Abby's question. There are actually some really good programs at most universities on how to lead meetings and conduct meetings. The kryptonite that I referred to earlier in my talk for me was related to that. And I had a bad habit of waiting to say something that would be really clever, and I would say it, and then I would follow it up, because it was so clever, with something really stupid. And that would derail meetings, and it would derail relationships. So, and that's just one example. That was my kryptonite that Angeletta told me about. She was Italian, so she used the term stupidaggine, which is much more colorful than, yeah. So you can get training in how to run meetings at your university. I don't know where you're at, but in Minnesota. I mean, there are definitely programs like that. Sometimes through the university, sometimes through Graduate Student Council, but you should definitely look for those. And it's a super important skill to be able to sit with a group of people and really listen to what they're saying and be able to incorporate that back. I mean, one way to say that is the LARA technique, where you listen, you affirm, you sort of renew, this LARA. You react to what they say, you listen to what they say, you affirm what they say, you react to it, and then you add to it, so that you're not driving the conversation, you're incorporating what everyone else is saying. So anyway, that's about public speaking and listening, really, really important. As far as leading a mission goes, you don't want to sort of jump into that too early in your career, because it is an incredibly time-consuming and emotionally draining thing. The first time that we proposed ELF in 2016, I had been the deputy PI on another mission. I had gotten a lot of experience with that. That really helped me. But I still totally freaked out halfway through the process when things were falling apart, because it's so complicated. You really want to start with research analysis proposals to NASA. You could start with small instrument proposals and then build to small missions, for example. And that way you build the experience without destroying yourself. I mean, being rejected after working for 2 years on something like this is really devastating. So you want to start with something where the stakes are not quite so high. That's what I would recommend. But I think it's great that you're interested in doing that, and hopefully there'll be many opportunities ahead. And there are new categories of planetary missions now, smaller than discovery missions at NASA, and that I think will really help build a much larger cadre of potential PIs for the bigger missions.
Thank you.
Yep. Okay. Yeah. Hi. I'm good. Does the microphone, the battery go out? Okay. There it is.
Yeah, I was just wondering for the future, like what finding would justify a landing mission on any of these moons?
Right.
And the role of privatization.
Okay, great.
It is. That's all I was wondering.
Those are both great questions. So one is, what would justify a lander and privatization? Okay, super. So for number one, I'll take Europa. And in the case of Europa, if the Europa Clipper is able to identify with its spectrometers places on the surface where there's fresh material, amino acids or organic compounds that have not been fried by radiation, then those are areas where material is regularly coming up from below. That is, Europa goes around in its eccentric orbit, which is what's responsible for, in part, for the ocean, the tidal heating. The cracks open and close, stuff comes out. If places can be identified where that material is coming out, and they're places where you can actually put a lander, that would really justify Europa lander. Enceladus, I think we can get a lot from a plume fly-through mission, so I think we really want to do that first. Privatization. So right now, the value proposition in spaceflight for doing deep space science is very, very difficult. You can justify, a business can justify getting involved in low Earth orbit and even lunar operations because there are lots of contracts available. But private industry actually does participate in very key aspects of these planetary missions, usually as subcontractors. So Honeybee Robotics, for example, which is was a relatively small company, is the company that designed this vacuum system for collecting material from the surface of Titan for Dragonfly. And so there is definitely, these days, role for small businesses as well as larger ones. Having a private company do a planetary mission, there have been a lot of false starts, including when I was at the University of Arizona. Whoever is there now, I saw her. Yep, hi. So there was an entrepreneur who had made a lot of money and came to the director of the lab and said that he was going to do a private asteroid mission. And the lab got involved with him, and it didn't, not only didn't it get off the ground, but it didn't even get to what we call phase A at that point. So it's economically, it's tough to really have private industry do the whole thing. Yep. Okay.
Respect the time of the OPAG meeting and our colleagues presenting there. So, but Mary Juliana has been waiting here. So we're going to give last question, and then we'll all head off to the
And
OPAG
I'll
meeting.
do a super short answer. So, good. Okay.
Could be a short question. So yeah, I go by Anna Whalen from Memorial University of Newfoundland. You talked a lot about your mentors, and I'm wondering if you have any insights of how you know a mentor is not for you.
So yes, you have to, so thank you, Anna. You have to really trust your early impressions of that mentor. You know, if that mentor is very dismissive or doesn't want to spend time or doesn't listen to you, those are real warning signs. It's really good to have some sort of a mentoring agreement or contract with your mentor. In some places that's required now, but you definitely want to test your mentor out by seeing if they're willing to draw up some kind of a mentoring agreement to deal with various things. If they say no, that's another warning sign. Some of these defects are fixable. You know, you might say to your mentor, you're really not paying attention to what I'm talking about. Maybe they'll correct it. But if you see that repeatedly, then you might want to go look for someone else. Thank you. All right. Okay. Thank you.